You drink it every day, you bathe in it. Your body is roughly 60% composed of it. Water seems ordinary, familiar, predictable, yet water is the most bizarre substance on Earth, and scientists have been arguing about its true nature for over a century. This transparent liquid breaks nearly every rule that governs how molecules should behave. It expands when it freezes. It becomes denser as it melts. Its boiling point defies prediction. It dissolves substances that should remain stubbornly insoluble. Water has confounded physics since researchers first tried to understand it at the molecular level, and the mystery only deepens the closer we look. There are at least 74 documented anomalies of water, properties that contradict the behavior of nearly every other substance known to science. Most liquids contract when they cool, becoming steadily denser until they solidify. Water does this too, but only down to 4 degrees Celsius. Below that temperature, something strange happens. The liquid begins expanding again, becoming less dense as it approaches the freezing point. This density maximum at 4 degrees Celsius has no parallel among common liquids. It ensures that ice floats on water instead of sinking, a property so crucial to life that if water behaved normally, every lake and ocean would freeze solid from the bottom up during winter, destroying aquatic ecosystems entirely. The anomalies extend far beyond density. Water has an extraordinarily high heat capacity, meaning it requires vast amounts of energy to change its temperature. This thermal inertia stabilizes Earth's climate and makes water an ideal coolant for everything from nuclear reactors to biological systems. The heat of vaporization is similarly excessive. Transforming liquid water into steam requires breaking hydrogen bonds that cling together with surprising tenacity, absorbing 44 kilojoules per mole at 25 degrees Celsius. For comparison, similar molecules like hydrogen sulfide require less than half that energy to vaporize. Surface tension provides another example. Water's surface behaves like an elastic membrane, strong enough to support insects and allow droplets to form nearly perfect spheres. This surface tension exceeds predictions based on molecular weight and structure. Viscosity follows an unusual temperature dependence. Compressibility shows a minimum at 46 degrees Celsius. Thermal conductivity rises to a maximum near 130 degrees Celsius. Even the speed of sound in water behaves oddly under certain conditions. Each anomaly demands explanation, and for over 100 years, those explanations have proven elusive. Understanding water requires examining its molecular architecture. The water molecule consists of one oxygen atom bonded to 2 hydrogen atoms, arranged in a distinctive V-shape rather than a straight line. This geometry arises from quantum mechanical principles governing how electrons distribute themselves around atoms. Oxygen has 6 electrons in its outer shell, needing 2 more to achieve stability. Each hydrogen provides 1 electron, forming covalent bonds. But oxygen also possesses 2 pairs of unshared electrons, called lone pairs, that occupy space and push the hydrogen atoms closer together through electrostatic repulsion. The bond angle between the 2 hydrogen atoms measures approximately 104.5 degrees, noticeably smaller than the 109.5 degrees of a perfect tetrahedron. This compression happens because the lone pairs spread their negative charge over greater volume than bonding pairs, creating stronger repulsion that squeezes the hydrogen atoms toward each other. The result is a bent molecule with a permanent electrical dipole. Oxygen, being highly electronegative, pulls shared electrons closer to itself, acquiring a partial negative charge. The hydrogen atoms consequently develop partial positive charges. This charge separation makes water a polar molecule, meaning it has distinct positive and negative regions despite being electrically neutral overall. The dipole moment of an isolated water molecule in the gas phase measures 1.85 debye units. When surrounded by other water molecules in the liquid phase, this dipole moment increases dramatically to roughly 2.6 debye units due to polarization effects. Neighboring molecules enhance each other's polarity through electrostatic interactions, a phenomenon known as cooperative polarization. Polarity enables hydrogen bonding, the interaction that defines water's behavior. A hydrogen bond forms when the partially positive hydrogen atom on one water molecule experiences electrostatic attraction to the partially negative oxygen atom on a neighboring molecule. This is not a true chemical bond like the covalent bonds within molecules. Instead, it represents a relatively weak intermolecular force, typically measuring about 23 kilojoules per mole in liquid water at 25 degrees Celsius. For comparison, the covalent oxygen-hydrogen bonds within a water molecule possess strengths around 492 kilojoules per mole, more than 20 times stronger. Yet despite being individually weak, hydrogen bonds collectively govern water's macroscopic properties. Each water molecule can potentially form 4 hydrogen bonds simultaneously, using its 2 hydrogen atoms as donors and its 2 lone pairs as acceptors. This tetrahedral coordination creates a 3-dimensional network extending throughout the liquid. In ice, every molecule achieves perfect tetrahedral bonding, locked into a crystalline lattice. In liquid water, thermal energy constantly disrupts this order, breaking and reforming hydrogen bonds on timescales of picoseconds. The geometric preference for tetrahedral coordination creates fundamental tension in liquid water. Thermal fluctuations prevent perfect tetrahedral arrangements, forcing molecules into various compromised configurations. Some molecules maintain nearly ideal tetrahedral geometry with 4 intact hydrogen bonds. Others adopt distorted arrangements with bent or stretched bonds. Still others lose 1 or more hydrogen bonds entirely, creating coordination defects. The liquid becomes a dynamic mosaic of different local structures, constantly shifting as molecules jostle and reorient. This structural diversity holds the key to water's anomalies. In the 1930s, scientists began proposing that water might not be a uniform liquid at all, but rather a mixture of distinct molecular arrangements coexisting in dynamic equilibrium. These mixture models suggested that some regions of water maintain ice-like structures with strong tetrahedral hydrogen bonding, while other regions adopt more collapsed, disordered configurations with weaker bonding. Temperature and pressure would shift the balance between these structural states, potentially explaining why water behaves so differently under varying conditions. The first rigorous mixture theory came from Wilhelm Röntgen in 1892, decades before hydrogen bonding was even recognized as a phenomenon. Röntgen, who would later discover X-rays, proposed that liquid water consists of 2 distinct molecular species in equilibrium. He imagined ice molecules, representing a more structured, lower density form, coexisting with simple molecules, representing a denser, less organized form. As temperature increased, ice molecules would convert into simple molecules, causing structural and volumetric changes. By adjusting the parameters of his model, Röntgen could explain the density maximum at 4 degrees Celsius, the minimum in compressibility, and several other anomalies. Röntgen's insight was prophetic, though his specific model lacked the molecular details that would emerge over subsequent decades. The true structure of ice remained unknown until 1929, when Barnes confirmed through X-ray measurements that ice forms a hexagonal crystal lattice with tetrahedral coordination. 4 years later, in 1933, John Desmond Bernal and Ralph Fowler revolutionized understanding of liquid water by applying newly developed quantum mechanics and X-ray scattering techniques to the structural problem. Bernal and Fowler recognized that water's V-shaped geometry and charge distribution implied specific patterns for how molecules would interact. They proposed that the positive charges on hydrogen atoms would align with negative charges on oxygen atoms' lone pairs, creating tetrahedral coordination patterns. By constructing theoretical models of different possible liquid structures and calculating their expected X-ray diffraction patterns, they could compare predictions with experimental measurements. This reverse engineering approach represented a major methodological advance. Their analysis suggested that liquid water exists in multiple structural forms depending on temperature. At low temperatures below 4 degrees Celsius, water predominantly adopts what they called Water 1, a tridymite ice-like structure with open tetrahedral networks. At ordinary temperatures, Water 2 dominates, featuring quartz-like arrangements. At high temperatures, Water 3 resembles a close-packed liquid similar to other simple molecular fluids. Crucially, Bernal and Fowler proposed that molecules interconvert between these forms rather than permanently remaining in distinct phases. This dynamic equilibrium concept became foundational to all subsequent mixture theories. The Bernal-Fowler model faced criticism and underwent extensive revision over following decades. Linus Pauling introduced clathrate-like cluster structures in 1959, suggesting that water might contain cage-like arrangements similar to gas hydrates. Harold Frank and Wen Yang developed the concept of flickering structures in 1957, proposing that hydrogen-bonded clusters form and dissolve on timescales of 10 to the negative 10th or 10 to the negative 11th seconds, intermediate between molecular vibrations and bulk relaxation times. These flickering structures provided a physical picture for how water could simultaneously exhibit liquid-like fluidity and solid-like structural correlations. By the 1960s and 70s, mixture models had evolved into explicit two-state theories. Scientists including Davis, Litovitz, and Angel formalized the idea that water contains two distinct structural populations: ice-like open hexagonal structures with low density and close-packed structures with high density. These two states would exist in temperature and pressure-dependent equilibrium, with their relative populations determining observable properties. When the low-density state dominates at low temperatures, water expands. When the high-density state takes over at higher temperatures, water contracts. The density maximum emerges naturally from the crossover point where these competing effects balance. Two-state models offered elegant explanations for many anomalies, but they remained controversial. Some physicists favored uniformist models treating all molecules as essentially equivalent, with properties arising from continuous distortions of hydrogen bonds rather than discrete structural states. The debate intensified throughout the late 20th century, with both approaches claiming experimental support. Resolution would require techniques capable of directly observing water's molecular structure with sufficient detail to distinguish between competing theories. Water is fighting itself at the molecular level, torn between the geometric demands of tetrahedral hydrogen bonding and the disruptive effects of thermal energy. This internal conflict generates the anomalous properties that make water essential to life and technology. Understanding this molecular civil war requires journeying through the history of discovery, the physics of hydrogen bonds, and the cutting-edge experiments that have finally revealed water's true nature. The story begins more than a century ago with a simple observation that something was deeply wrong with our understanding of this most common substance. Chapter 2: The discovery of water's split personality. The density maximum of water at 4 degrees Celsius was known long before anyone understood why it existed. Early scientists measured this property through careful experiments, observing that water reaches its highest density slightly above the freezing point, before expanding both when cooled further toward ice and when heated toward boiling. This behavior stood in stark contrast to virtually all other liquids, which contract monotonically as temperature decreases until solidification. The anomaly demanded explanation, yet the molecular tools necessary for understanding remained decades in the future. Wilhelm Röntgen's 1892 proposal that water consists of two distinct molecular forms marked the beginning of serious theoretical attempts to explain water's peculiarities. Röntgen suggested that liquid water represented a saturated solution of ice molecules dissolved in a matrix of simple molecules. The concentration of ice molecules would depend on temperature and pressure, increasing at lower temperatures and decreasing as temperature rose. The ice molecules, being less dense than simple molecules, would occupy greater volume. This structural hypothesis could account for the density maximum by proposing that below 4 degrees, the proportion of ice molecules increases rapidly enough to cause overall expansion despite ongoing thermal contraction of each molecular type. Röntgen extended his model to explain additional anomalies. The compressibility minimum could arise from competition between the two molecular forms, which would respond differently to pressure. Ice molecules, with their open structures, would be more compressible than compact simple molecules. At the compressibility minimum, the changing ratio of the two forms would exactly compensate for the intrinsic compressibility of each type. Similarly, the decrease in viscosity under pressure and the depression of the freezing point under high pressure could both result from pressure favoring simple molecules over ice molecules, altering the mixture's bulk properties. The Röntgen mixture theory represented remarkable insight for its time, but it contained no mechanistic details about what distinguished ice molecules from simple molecules at the atomic level. In 1892, the electron had not yet been discovered. Atomic structure remained mysterious. The concept of hydrogen bonding would not emerge until the 1920s. Röntgen worked purely from thermodynamic principles and macroscopic observations, constructing a phenomenological model that fit experimental data without explaining the underlying molecular physics. The situation changed dramatically in the early 20th century as quantum mechanics revolutionized chemistry and physics. By the 1920s, scientists understood that molecules consisted of atoms held together by electron sharing or transfer. The hydrogen molecule was recognized as two hydrogen atoms sharing electrons in a covalent bond. Water's molecular formula as H2O was firmly established, though the three-dimensional arrangement of atoms remained uncertain. Spectroscopic measurements provided clues about molecular geometry, but direct structural determination awaited the development of X-ray and neutron scattering techniques. In 1932, the V-shaped geometry of the water molecule was conclusively established through spectroscopy and quantum mechanical calculations. This discovery proved crucial because it immediately implied that water molecules could not pack together like spheres or simple ellipsoids. The bent shape and resulting dipole moment meant that electrostatic forces would strongly influence how molecules oriented relative to each other. The polarity of water became recognized as fundamental to its behavior, though the full implications took years to appreciate. John Desmond Bernal, a physicist with broad interests spanning crystallography, molecular biology, and social issues, became fascinated with water structure in the early 1930s. Working at Cambridge University, Bernal had access to X-ray diffraction equipment and was among the pioneers applying this technique to study liquids. The X-ray scattering patterns from liquids looked entirely different from the sharp spots produced by crystals. Instead of discrete reflections indicating regular atomic arrangements, liquids produced diffuse rings corresponding to statistical averages of distances between molecules. Interpreting these patterns required sophisticated mathematical methods. Zernike and Prinz had shown in the 1920s that X-ray scattering intensity from a liquid could be mathematically related to the radial distribution function, which describes the probability of finding a molecule at various distances from a central reference molecule. For an ideal gas with no intermolecular forces, this function would be flat, indicating equal probability at all distances. For a liquid, the function oscillates, showing peaks corresponding to preferred neighbor separations and valleys indicating excluded regions. The first peak reveals the typical spacing between adjacent molecules, while subsequent peaks provide information about longer-range order. Bernal recognized that rather than trying to extract structure from scattering patterns through complex mathematical inversion, he could work backward, by constructing physical or computational models of possible liquid structures based on theoretical considerations. He could calculate what X-ray scattering pattern each model would produce, then compare predictions with experimental measurements. The model that best reproduced observed scattering would most likely represent the true liquid structure. This approach required making informed guesses about plausible molecular arrangements, but it avoided the mathematical ambiguities of direct pattern inversion. In 1933, Bernal and his colleague Ralph Fowler published their landmark analysis in the very first year of the Journal of Chemical Physics. They began by considering what the newly determined V-shaped geometry implied for intermolecular interactions. Using early quantum mechanics, Bernal argued that the charge distribution in water could be represented as positive charges on the hydrogen atoms and negative charges located behind the oxygen atom, creating 4 lobes arranged tetrahedrally. 2 lobes correspond to the hydrogen atoms themselves, pointing outward from the oxygen. The other 2 correspond to the lone pair electrons, pointing in opposite directions. This tetrahedral charge distribution suggested that water molecules would prefer to coordinate with 4 neighbors, each positioned to maximize electrostatic attraction between opposite charges. One molecule's hydrogen atoms would align with neighboring molecules' lone pairs, while its own lone pairs would attract neighboring molecules' hydrogens. The resulting network would resemble crystal structures like ice, tridymite, or quartz, all of which feature tetrahedral coordination patterns. However, thermal energy in the liquid would prevent perfect crystalline order, creating distorted and fluctuating versions of these motifs. Bernal and Fowler constructed 3 structural models corresponding to different temperature regimes. Their Water 1 model featured tridymite ice-like structures with open tetrahedral hydrogen bonding networks. This low-density arrangement would dominate at temperatures below 4 degrees Celsius, where water is coldest without freezing. Water 2 adopted quartz-like structures, still tetrahedral but with different topology, dominating at ordinary room temperatures. Water 3 represented high-temperature water approaching the boiling point, where thermal disruption breaks down tetrahedral order, producing close-packed arrangements similar to simple liquids like argon or methane. For each model, they calculated the expected X-ray scattering pattern based on the positions and orientations of molecules in their proposed structures. Comparing these theoretical patterns with experimental measurements from Amaldi and others revealed that the quartz-like Water 2 model provided the best match at room temperature. The tridymite ice-like structure fit better for cold water, while the close-packed structure matched high-temperature data. This suggested that water indeed transitions between distinct structural forms as temperature changes. Critically, Bernal and Fowler proposed that molecules continuously interconvert between these structural states rather than existing as separate phases. At any given temperature, water would contain a mixture of molecules in different local environments, with the equilibrium composition shifting as conditions changed. This dynamic picture contrasted with earlier static mixture models like Röntgen's, which implied coexisting populations of permanently different molecular types. The Bernal-Fowler model recognized that thermal fluctuations constantly break and reform hydrogen bonds, allowing individual molecules to sample different structural configurations on rapid timescales. The proposal that water contains multiple coexisting structural forms with different densities provided a natural explanation for the density maximum. At temperatures well above 4 degrees, most molecules adopt relatively compact, high-density configurations. As water cools toward 4 degrees, thermal contraction reduces volume in the normal manner. Below 4 degrees, however, molecules increasingly adopt open, low-density tetrahedral structures resembling ice. This structural transition toward lower-density configurations overwhelms ordinary thermal contraction, causing water to expand. The density maximum at 4 degrees represents the crossover point where these opposing effects balance. Bernal and Fowler's work established tetrahedral hydrogen bonding as the central organizing principle of water structure. Yet their model remained qualitative and imprecise by modern standards. They could not specify exactly how many molecules occupied each structural state at a given temperature, nor could they calculate thermodynamic properties from first principles. The mathematical tools and computational power needed for quantitative molecular modeling would not become available for several more decades. Their contribution was primarily conceptual, establishing a framework that subsequent researchers would refine and test. The Bernal-Fowler model faced immediate challenges. Some scientists argued that X-ray scattering patterns could be explained without invoking multiple structural states. Perhaps a single type of distorted hydrogen bond network, continuously varying with temperature, could account for observations. John Pople proposed such a model in 1951, describing a continuum of angular distortions rather than discrete structural states. Despite showing poor agreement with detailed radial distribution functions, Pople's one-state continuum model attracted significant support among physicists who found mixture theories conceptually uncomfortable. The debate between mixture models and continuum models would persist for decades, shaped partly by disciplinary perspectives. Chemists generally favored mixture models, finding it natural to think of molecules adopting different conformations or configurations. Physicists often preferred continuum models, viewing the liquid as a single phase with smoothly varying properties. Both approaches could fit certain experimental data, making decisive tests difficult. Resolution required measurements sensitive to the specific structural features, distinguishing the competing theories. Throughout the mid-20th century, additional evidence accumulated suggesting heterogeneous structure in liquid water. Raman spectroscopy, which probes molecular vibrations, revealed multiple spectral features that appeared to correspond to different hydrogen bonding environments. Walrafen's studies in 1968 and subsequently showed that the Raman spectrum could be decomposed into components attributable to strongly bonded and weakly bonded water molecules. The temperature dependence of these components matched expectations for an equilibrium mixture of distinct structural states. Dielectric relaxation measurements provided complementary information. Water molecules are permanent dipoles that rotate in response to applied electric fields. The time required for this orientational relaxation depends on the local environment surrounding each molecule. If all molecules experienced identical environments, relaxation would follow a single exponential decay. Instead, measurements revealed more complex behavior consistent with molecules occupying multiple environments with different relaxation characteristics. This supported the idea that water contains structural heterogeneity. Nuclear magnetic resonance spectroscopy added another perspective. The NMR signal from hydrogen nuclei in water molecules depends sensitively on the electronic environment, which is influenced by hydrogen bonding. Early NMR studies detected signatures consistent with multiple hydrogen bonding states. As the technique improved through the latter 20th century, more detailed information about hydrogen bond distributions became accessible, generally supporting the existence of distinct structural populations. Despite accumulating spectroscopic evidence, skepticism about two-state models persisted. Critics noted that spectral features attributed to different structural states might instead reflect continuous distributions of bond strengths and angles. Decomposing spectra into discrete components involved some degree of arbitrary choice about how many components to include and how to define boundaries between them. More direct structural probes were needed, ideally techniques that could visualize the three-dimensional arrangement of molecules and unambiguously identify distinct local structures. The development of powerful computer simulations in the late 20th century provided a new approach to understanding water structure. By numerically solving the equations governing molecular motion for thousands of interacting water molecules, researchers could generate detailed trajectories showing how molecules move and interact over time. These simulations required accurate mathematical models of the forces between molecules, called force fields or potential energy functions. Early water models were crude, but by the 1990s and 2000s, sophisticated models like TIP4P and TIP5P could reproduce many experimental properties with impressive accuracy. Molecular dynamics simulations revealed that water indeed contains significant structural heterogeneity. At any instant, some molecules maintain nearly perfect tetrahedral coordination with 4 hydrogen bonds, while others adopt distorted geometries with fewer or bent bonds. Calculating structural order parameters from simulations allowed quantification of how much tetrahedral structure existed at different temperatures and pressures. These analyses consistently showed that tetrahedral order decreases with increasing temperature, exactly as mixture theories predicted. More dramatically, simulations in the early 21st century began revealing evidence for a liquid-liquid phase transition in deeply supercooled water, a phenomenon that would conclusively validate the two-state picture. Before examining those breakthrough discoveries, we must understand the battlefield where this molecular conflict plays out. Hydrogen bonds are the forces that create structure in water, and their peculiar properties determine everything about how water behaves. Chapter 3: Hydrogen bonds, the battlefield. Hydrogen bonds are not true chemical bonds. This crucial distinction confused scientists for decades after the phenomenon was first recognized. A chemical bond involves sharing or transferring electrons between atoms, creating stable molecular structures held together by quantum mechanical forces. The covalent bonds linking hydrogen to oxygen within a water molecule are chemical bonds, requiring hundreds of kilojoules per mole to break. Hydrogen bonds are far weaker, representing electrostatic attractions between molecules rather than within them. Yet these weak intermolecular forces collectively determine nearly every property that makes water unique. The hydrogen bond in water forms because of the molecule's polar nature. Oxygen's high electronegativity pulls shared electrons away from hydrogen atoms, leaving the hydrogens electron deficient with partial positive charges. Meanwhile, oxygen accumulates excess electron density, particularly in the lone pair regions, creating partial negative charges. When two water molecules approach each other in favorable orientations, the positive hydrogen of one molecule experiences electrostatic attraction to the negative oxygen region of the other. This attraction constitutes the hydrogen bond. The strength of a typical hydrogen bond in liquid water at 25 degrees Celsius measures approximately 23 kilojoules per mole, though estimates vary depending on measurement method and precise definition. Some calculations based on the enthalpy of vaporization suggest values around 20 kilojoules per mole, while spectroscopic measurements can indicate values closer to 25 kilojoules per mole. The uncertainty reflects genuine ambiguity about what exactly constitutes breaking a hydrogen bond. In liquid water, hydrogen bonds are constantly distorting, stretching, and partially breaking before reforming. Defining a sharp threshold between bonded and non-bonded states involves some arbitrariness. For comparison, thermal energy at room temperature averages only about 2.5 kilojoules per mole, meaning a typical hydrogen bond is roughly 9 times stronger than random thermal collisions. This explains why hydrogen bonds significantly influence water's structure despite thermal disruption. They are strong enough to persist for meaningful durations, but weak enough to break and reform rapidly. The balance between bond strength and thermal energy creates dynamic structure where patterns exist but constantly fluctuate. Ice provides a useful reference point for understanding hydrogen bonding in liquid water. In hexagonal ice, the most common ice form at atmospheric pressure, every water molecule forms exactly 4 hydrogen bonds in perfect tetrahedral arrangement. 2 bonds involve the molecule's hydrogen atoms as donors, pointing toward neighboring oxygens. 2 bonds involve the molecule's oxygen lone pairs as acceptors, receiving hydrogen atoms from neighbors. This fourfold coordination creates an open crystalline lattice with low density, explaining why ice floats on water. The hydrogen bond energy in ice is slightly stronger than in liquid water, estimated at approximately 26 to 28 kilojoules per mole at 0 Kelvin, when correcting for all interactions including non-bonded terms. This roughly 3 kilojoule per mole difference reflects the fact that ice's perfectly optimized geometry allows stronger bonding than the distorted arrangements forced upon liquid water molecules by thermal motion. The OH covalent bonds within molecules are correspondingly about 4 picometers longer in liquid water than in ice, indicating that strong hydrogen bonding in ice slightly weakens the intramolecular bonds. When ice melts, the perfect tetrahedral network breaks down. Thermal energy at 0 degrees Celsius becomes sufficient to disrupt some hydrogen bonds, allowing molecules to move more freely. Interestingly, the initial effect of melting is to increase density rather than decrease it. This counterintuitive behavior occurs because thermal vibrations in ice create a structure with more open space than necessary. When melting begins, some molecules can collapse into the cavities of the tetrahedral network, increasing packing efficiency. The coordination number, meaning the average number of nearest neighbors, increases slightly from 4 in ice to around 4.7 in liquid water at 0 degrees. This increased coordination seems paradoxical. If molecules gain an extra neighbor or two, wouldn't that require more hydrogen bonds? The resolution lies in recognizing that not all nearest neighbors form hydrogen bonds. In ice, the 4 nearest neighbors are also the 4 hydrogen bonding partners. In liquid water, molecules can have close neighbors without optimal hydrogen bonding geometry. Some molecules squeeze into positions where they interact through weaker, non-directional van der Waals forces rather than strong, directional hydrogen bonds. The average number of hydrogen bonds per molecule in liquid water is typically estimated at around 3.5 to 3.7 at room temperature, fewer than the 4 in ice despite higher coordination numbers. The geometry of hydrogen bonding matters enormously. Maximum bond strength occurs when the hydrogen atom lies along a straight line connecting the donor oxygen and acceptor oxygen atoms, forming a 180-degree angle. Any deviation from linearity weakens the bond because the optimal overlap between the hydrogen's electron-deficient region and the acceptor's electron-rich lone pair decreases. In liquid water, most hydrogen bonds are bent to some degree. The distribution of angles is broad, with some bonds nearly linear and others bent by 30 or 40 degrees or more. Similarly, the distance between oxygen atoms in hydrogen-bonded pairs affects bond strength. In ice, the O distance measures approximately 2.75 angstroms. In liquid water, the first peak of the oxygen-oxygen radial distribution function centers near 2.85 angstroms at room temperature, slightly longer than in ice. This stretched distance indicates weaker average hydrogen bonding. However, the first peak is quite broad, meaning significant variation exists. Some hydrogen bonds are shorter and stronger than the average, while others are longer and weaker. The lifetime of individual hydrogen bonds in liquid water is remarkably short. Early estimates by Frank and Wen suggested durations around 1/10 to 100th of a picosecond, meaning 10 to the negative 11th or 10 to the negative 12 seconds. More recent simulations and experimental measurements indicate that while very fast fluctuations occur on these timescales, more meaningful structural relaxation happens over 1 to 10 picoseconds. A hydrogen bond typically survives for a few picoseconds before breaking due to molecular reorientations, then reforms on similar timescales as molecules jostle into new configurations. This rapid breaking and reforming creates what Frank and Wen famously called flickering structures. At any given instant, water contains hydrogen-bonded networks with moderate coherence extending over several molecular diameters. A picosecond later, these specific networks have dissolved, but new ones with similar statistical properties have formed elsewhere. The liquid maintains structural correlations while constantly reconfiguring. Like a kaleidoscope that always shows patterns, but never the same pattern twice. This dynamic picture reconciles water's liquid fluidity with its ice-like structural motifs. The energy required to break a hydrogen bond comes from thermal fluctuations. At room temperature, molecules possess kinetic energy averaging about 4 kilojoules per mole of translational motion, plus additional energy in rotational and vibrational modes. Occasionally, random thermal motion provides enough energy to overcome the 23 kilojoule per mole attraction of a hydrogen bond. The probability of such fluctuations follows Boltzmann's statistics, meaning higher energy events occur less frequently. Stronger hydrogen bonds break less often than weaker ones, creating a distribution of bond lifetimes. Hydrogen bond breaking and formation are not independent random events. The breaking of one bond typically facilitates formation of new bonds because molecular reorientation that disrupts one interaction can simultaneously optimize another. This cooperativity means that hydrogen bond dynamics involve collective rearrangements of multiple molecules rather than isolated single bond events. Networks of 4, 5, or 6 molecules might collectively reorganize on picosecond timescales, with breaking bonds in one region of the cluster compensated by strengthening bonds elsewhere. The tetrahedral geometry preferred by hydrogen bonding creates geometric frustration in liquid water. Perfect tetrahedral coordination requires specific angles and distances that cannot always be simultaneously satisfied when molecules are packed into liquid densities. Consider a central water molecule attempting to hydrogen bond with 4 neighbors in perfect tetrahedral arrangement. Each neighbor also wants 4 tetrahedral partners, creating competing geometric demands. The resulting structure must compromise, accepting some distorted bonds to accommodate all the constraints. This frustration prevents water from adopting a single perfect structure, instead forcing it to sample various imperfect configurations. One way to visualize this compromise involves distinguishing between different types of local environments. Some molecules successfully maintain nearly ideal tetrahedral coordination with 4 reasonably strong hydrogen bonds arranged at close to 109-degree angles. These molecules exist in ice-like or low-density environments, occupying more volume due to the open tetrahedral geometry. Other molecules adopt more collapsed configurations with distorted hydrogen bonds and possibly only 3 strong bonds plus a weaker interaction. These exist in dense or close-packed environments, taking up less volume per molecule. The two-state model of water structure formalizes this picture. Rather than viewing water as containing a continuous spectrum of local environments, the model approximates the distribution as bimodal, consisting predominantly of 2 types of configurations. The low-density state or low-density liquid, abbreviated LDL, features strong tetrahedral hydrogen bonding with 4 intact bonds per molecule on average. The high-density state or high-density liquid, abbreviated HDL, involves weaker, more distorted bonding with collapsed structures. Individual molecules fluctuate between these states as thermal energy breaks and reforms hydrogen bonds. The relative populations of LDL and HDL configurations depend on temperature and pressure. At low temperatures, LDL dominates because strong hydrogen bonding is thermodynamically favorable and thermal energy is insufficient to disrupt tetrahedral structures. As temperature increases, entropy favors the more disordered HDL state, shifting the equilibrium. Pressure also affects the balance because LDL structures occupy more volume than HDL structures. Applying pressure raises the chemical potential of LDL relative to HDL, driving molecules toward denser configurations. This competition between LDL and HDL states creates most of water's anomalous properties. The density maximum at 4 degrees emerges because below 4 degrees, LDL becomes increasingly dominant, and its lower density causes overall expansion that overcomes normal thermal contraction. Above 4 degrees, HDL dominates and normal liquid behavior resumes. Heat capacity anomalies arise because energy goes into converting between structural states as well as into molecular kinetic energy. Compressibility anomalies reflect the different compressibilities of LDL and HDL structures and how their ratio changes with pressure. The two-state picture is an approximation. Real liquid water contains a distribution of local structures, not just 2 discrete types. However, computational and experimental evidence increasingly supports the idea that this distribution is indeed bimodal rather than smoothly unimodal. Molecules cluster around 2 favored configurations corresponding to LDL and HDL, with relatively few molecules in intermediate states. The bimodal nature justifies treating water as a mixture of 2 distinct structural populations in dynamic equilibrium. Quantifying the degree of tetrahedral structure in different local environments requires defining order parameters. One widely used measure is the tetrahedral order parameter, which quantifies how closely the angles between a central molecule and its 4 nearest neighbors match the perfect tetrahedral angle of 109.5 degrees. A perfectly tetrahedral arrangement yields an order parameter of 1, while a random arrangement gives 0. Computing this parameter from simulations or deducing it from experiments allows tracking how much tetrahedral structure exists at different conditions. Studies consistently show that the tetrahedral order parameter decreases with increasing temperature and increasing pressure, exactly as expected if LDL populations decline under those conditions. At very low temperatures approaching the glass transition, most molecules exhibit high tetrahedral order. At high temperatures near boiling, order decreases substantially, though never vanishes completely. This continuous variation reflects the shifting equilibrium between structural states as conditions change. The hydrogen bond network in water also exhibits spatial heterogeneity. Some regions of the liquid contain clusters of highly coordinated molecules with strong tetrahedral bonding, while nearby regions show more disrupted structures. These regions fluctuate on picosecond timescales, but at any instant, the liquid appears patchy rather than uniform. The spatial scale of these heterogeneities extends to roughly 1 to 2 nanometers, involving perhaps 10 to 50 molecules per coherent domain. This mesoscopic structure between molecular and macroscopic scales has proven difficult to measure directly, but appears consistently in simulations. Understanding the hydrogen bond battlefield requires appreciating both the weakness and the importance of these interactions. At 23 kilojoules per mole, an individual hydrogen bond barely withstands thermal buffeting at room temperature. Yet because each molecule participates in multiple bonds, the collective network possesses significant resilience. Breaking all hydrogen bonds holding a molecule in place requires overcoming the cumulative strength of 3 to 4 bonds simultaneously, totaling 70 to 90 kilojoules per mole. This collective effect explains why water's heat of vaporization reaches 44 kilojoules per mole, far exceeding the strength of single hydrogen bonds. The battlefield metaphor captures the adversarial relationship between competing structural tendencies in water. Hydrogen bonding favors tetrahedral order and low density. Thermal energy favors disorder and high density. Pressure favors collapse and high density. Temperature and pressure manipulate the outcome of this conflict, tipping the balance between structural states. Water's anomalous properties emerge as casualties and consequences of this ongoing war, macroscopic reflections of molecular-scale conflict. Understanding who wins under what conditions requires examining each structural state in detail, beginning with the low-density liquid that tries to maintain ice-like order in the chaotic thermal battlefield. The low-density liquid represents water's attempt to preserve ice-like order in the chaotic thermal environment of the liquid phase. This structural form, abbreviated LDL, embodies the tetrahedral coordination that hydrogen bonding naturally prefers. In LDL domains, molecules arrange themselves with nearly ideal geometry, each forming 4 hydrogen bonds directed toward the corners of an imaginary tetrahedron. 2 bonds involve the molecule donating its hydrogen atoms to neighboring oxygen lone pairs. 2 bonds involve the molecule accepting hydrogen atoms from neighbors onto its own lone pairs. This fourfold symmetry creates open, cage-like networks reminiscent of ice's crystalline architecture. The defining characteristic of LDL is its low density, typically around 0.94 grams per cubic centimeter when measured as pure low-density amorphous ice at 77 Kelvin and atmospheric pressure. This density is remarkably similar to ordinary ice, which measures 0.92 grams per cubic centimeter. The similarity is no coincidence. Both structures maintain extensive tetrahedral hydrogen bonding that prevents molecules from packing efficiently. The open cages and channels inherent to tetrahedral networks waste volume compared to close-packed arrangements. This inefficiency manifests as low density, but it provides stability through strong, geometrically optimized hydrogen bonds. Tetrahedral coordination in LDL means that the oxygen-oxygen distance between bonded neighbors centers around 2.75 angstroms, matching the spacing in hexagonal ice. X-ray diffraction patterns from LDL show a prominent first peak at a scattering vector Q of approximately 1.7 inverse angstroms, corresponding to this nearest neighbor separation. The peak's sharpness indicates that these distances are relatively uniform, with most molecules maintaining similar spacing to their bonded neighbors. This structural regularity distinguishes LDL from more disordered liquid forms. The angular distribution of bonds in LDL also reflects tetrahedral preferences. The oxygen-oxygen-oxygen angle between a central molecule and two of its neighbors averages close to 109.5 degrees, the exact tetrahedral angle. Some molecules achieve nearly perfect tetrahedral geometry, while others show modest distortions of 5 to 10 degrees. This distribution is much narrower than in high-density liquid, where angular disorder reaches 30 degrees or more. The tighter angular constraints in LDL preserve the directional character of hydrogen bonds, maintaining strong electrostatic overlap between donor hydrogens and acceptor lone pairs. Beyond the first coordination shell containing the four nearest neighbors, LDL exhibits substantial structural order extending to second and third shells. The second shell, containing molecules at distances around 4.5 angstroms from a central molecule, shows clear peaks in radial distribution functions. These second neighbors occupy positions that make geometric sense given the tetrahedral arrangement of first neighbors. If you imagine a central molecule surrounded by four tetrahedrally arranged neighbors, the second shell naturally forms as each first shell neighbor contributes its own tetrahedral partners. This creates a coherent network rather than random positioning. The extent of structural correlations in LDL can be quantified through the correlation length, which measures how far tetrahedral order persists before dissolving into disorder. In LDL, correlation lengths reach approximately 11 angstroms or more, encompassing roughly 10 to 20 molecules. This means that if you identify one molecule in a tetrahedral environment, you can predict with reasonable accuracy the positions and orientations of neighbors up to 11 angstroms away. Such long-range correlations are remarkable for a liquid and reflect the strength of cooperative hydrogen bonding that propagates order through multiple coordination shells. Molecular dynamics simulations provide detailed pictures of LDL structure by tracking individual molecules over time. These simulations reveal that LDL molecules spend most of their time with four intact hydrogen bonds, breaking them only briefly before reforming. The hydrogen bond lifetime in LDL exceeds 5 picoseconds on average, significantly longer than in normal liquid water at room temperature, where lifetimes drop to around 2 picoseconds. This increased stability reflects the better geometric optimization that tetrahedral environments allow. Well-aligned bonds resist thermal disruption more effectively than distorted bonds. The energetics of LDL favor its formation at low temperatures. Each molecule in LDL gains approximately 25 kilojoules per mole from its four hydrogen bonds, totaling roughly 100 kilojoules per mole when divided among all participants. This strong bonding lowers the enthalpy compared to less organized states. However, LDL pays an entropic cost. The rigid tetrahedral constraints limit the number of configurations molecules can adopt. Entropy measures the logarithm of available configurations, so fewer configurations mean lower entropy. At low temperatures, where enthalpy dominates the free energy, LDL's strong bonding wins. At high temperatures, where entropy becomes more important, the configurational restrictions make LDL unfavorable. The transition temperature, where LDL becomes preferred over high-density liquid, depends on pressure. At atmospheric pressure, computer simulations using models like TIP4P suggest that LDL dominates below approximately 220 Kelvin. This temperature lies well into the supercooled regime, below water's normal freezing point of 273 Kelvin. Supercooling is necessary to access LDL because at higher temperatures, ice crystallization occurs before LDL populations grow large enough to dominate. The region between normal freezing and the temperature where LDL becomes stable has been called no man's land because crystallization typically prevents experimental access. Pressure dramatically affects LDL stability because LDL has low density and occupies large volume. Increasing pressure raises its chemical potential relative to denser forms. Think of pressure as a tax on volume. The more volume a structure occupies, the higher the tax. LDL pays a heavy volume tax at high pressures, making it thermodynamically unfavorable. Computer simulations show that the pressure range where LDL can exist as a stable or metastable phase extends only up to about 50 to 100 megapascals, roughly 500 to 1,000 atmospheres. Above these pressures, the volume penalty becomes too severe, and water adopts denser configurations regardless of temperature. The liquid-liquid critical point, if it exists, marks the boundary where LDL and high-density liquid become indistinguishable. Below the critical temperature, LDL and HDL can coexist as separate phases with a distinct interface between them, like oil and water separating. Above the critical temperature, the distinction blurs and water transitions continuously between LDL-like and HDL-like regions without phase separation. The critical point is predicted to occur near 198 Kelvin and approximately 1,250 atmospheres, according to recent simulations using the MBPOL potential energy model. This location sits in no man's land, making direct experimental confirmation extremely challenging. Creating pure LDL in the laboratory requires avoiding crystallization. One successful approach involves hyperquenching, cooling water at rates exceeding 1 million Kelvin per second. Such extreme cooling rates bypass the temperature range where ice nuclei can form and grow. The result is low-density amorphous ice, abbreviated LDA, which represents glassy LDL, frozen before molecules could arrange into crystalline patterns. LDA forms at atmospheric pressure when thin films or droplets of water are deposited onto surfaces cooled to 77 Kelvin, the boiling point of liquid nitrogen. The resulting amorphous solid has the density and local structure of LDL, but lacks long-range periodicity. Characterizing LDA through X-ray and neutron diffraction reveals its structural similarity to LDL. The oxygen-oxygen radial distribution function shows the characteristic first peak at 2.75 angstroms and a well-defined second peak at 4.5 angstroms, matching tetrahedral expectations. The absence of sharp Bragg peaks that would indicate crystallinity confirms the amorphous nature. When LDA is slowly warmed above its glass transition temperature of approximately 136 Kelvin, it transforms into supercooled liquid water, presumably with high LDL content, before crystallizing around 150 to 160 Kelvin. Another method for studying LDL-like structures involves confinement in nanopores or emulsions. When water is trapped in pores smaller than the critical nucleus size for ice formation, crystallization can be suppressed, allowing supercooled liquid to persist at temperatures where bulk water would freeze. Research groups have used hydrophilic silica pores with diameters of 1 to 2 nanometers to stabilize water down to temperatures approaching 180 Kelvin. Spectroscopic measurements on confined water show signatures consistent with increased tetrahedral ordering as temperature drops, suggesting that LDL populations grow in these systems. Experiments using ultrafast lasers have recently provided the most direct evidence for LDL in bulk water. In 2018, researchers at Stockholm University, led by Anders Nilsson, developed techniques to probe deeply supercooled water using femtosecond X-ray pulses. They prepared samples by compressing high-density amorphous ice to high pressure, then heating it rapidly with infrared laser pulses to create liquid water under pressure. By carefully tuning the pressure and temperature, they accessed conditions where LDL should exist. X-ray scattering measurements revealed structures with pronounced tetrahedral order, matching theoretical predictions for LDL. The observation confirmed that LDL represents a real structural state, not merely a theoretical construct. The properties of LDL differ markedly from normal liquid water. Its lower density obviously distinguishes it, but other characteristics also diverge. LDL exhibits higher viscosity than equally cold HDL because the rigid tetrahedral networks resist flow. Imagine trying to pour a liquid whose molecules are locked into cage structures versus one with fluid, adaptable arrangements. The caged structure moves more sluggishly. Diffusion coefficients in LDL are correspondingly lower, meaning molecules migrate through the liquid more slowly. Self-diffusion in LDL at 200 Kelvin is estimated at around 1/10 the value in HDL at the same temperature. The dielectric constant of LDL, which measures how well the liquid screens electric fields, also exceeds that of HDL. This happens because the open tetrahedral structure allows greater polarizability. Water molecules can reorient their dipoles more freely when not tightly packed, leading to stronger collective responses to applied fields. Measurements on confined water and amorphous ices support this prediction, showing that dielectric constants increase as tetrahedral order grows. The difference is not enormous, perhaps 10 to 20%, but it is measurable and consistent with structural models. Heat capacity in LDL shows unusual temperature dependence related to the structural equilibrium with HDL. As temperature increases, some LDL molecules convert to HDL configurations. This conversion absorbs energy beyond what pure molecular heating would require, increasing the apparent heat capacity. Near the liquid-liquid transition, where conversion rates are highest, heat capacity can spike dramatically. This effect contributes to the well-known heat capacity maximum observed in supercooled water around 220 Kelvin at atmospheric pressure. The maximum represents the system's strong response to thermal energy, with much of that energy going into structural rearrangements rather than kinetic motion. Spectroscopic signatures help identify LDL in mixed populations. Raman spectroscopy, which measures molecular vibrations, shows that LDL exhibits a strong peak around 3,200 wave numbers, corresponding to oxygen-hydrogen stretching vibrations in strongly hydrogen-bonded environments. This peak is sharper and more intense in LDL than in HDL, where weaker and more variable bonding produces broader, red-shifted features. Infrared spectroscopy similarly distinguishes LDL through absorption bands that reflect the uniform, strong hydrogen bonds characteristic of tetrahedral networks. The existence of LDL helps explain numerous water anomalies beyond density. Compressibility, which measures volume change under pressure, behaves strangely in water. At normal temperatures, water's compressibility decreases as temperature rises, opposite to most liquids. This anomaly arises because increasing temperature shifts the equilibrium from LDL to HDL. Since LDL is more compressible due to its open structure, reducing LDL content by heating decreases overall compressibility. At very high temperatures, where LDL is nearly absent, normal liquid behavior resumes, and compressibility increases with temperature as expected. The thermal expansivity of water, which describes volume change with temperature, also reflects LDL-HDL competition. Below 4 degrees Celsius, cooling water increases LDL populations faster than thermal contraction reduces volume, causing overall expansion. This produces the famous density maximum. Above 4 degrees, thermal contraction dominates and water behaves normally. The balance point at 4 degrees represents the temperature where the two effects exactly compensate. This explanation, rooted in structural equilibrium, provides mechanistic understanding that purely thermodynamic models lack. Understanding LDL requires recognizing it as a thermodynamic state rather than a permanent molecular species. Individual molecules constantly fluctuate between LDL-like and HDL-like environments on picosecond timescales. The distinction becomes meaningful only when considering populations and averages over many molecules and longer times. At any instant, a snapshot would show a heterogeneous mixture of molecules in various local environments. Over time, statistical preferences emerge. At low temperatures and pressures, most molecules spend most of their time in LDL-like configurations. The liquid acts as though it contains substantial LDL content, even though no individual molecule permanently belongs to that state. This dynamic picture reconciles earlier debates about whether water contains distinct structural species or merely shows continuous variation. Both perspectives contain truth. Locally and instantaneously, continuous variation exists. Globally and statistically, distinct populations emerge. The two-state model captures the statistical reality while acknowledging underlying continuous dynamics. LDL and HDL represent basins in the free energy landscape where molecules preferentially reside, separated by barriers that molecules occasionally cross through thermal fluctuations. The LDL state represents water's attempt to maintain order, to preserve the beautiful tetrahedral symmetry that hydrogen bonding naturally creates. It is the structured warrior in the two-liquid war, fighting to impose geometric regularity against the chaos of thermal motion. At low temperatures, this warrior dominates, creating a liquid that resembles ice in structure, though not in dynamics. As temperature and pressure increase, the structured warrior loses ground to its rival, the disordered champion that thrives on chaos and density. Understanding this rival requires examining the high-density liquid state that emerges when tetrahedral order collapses. Chapter 5: High-Density Liquid, the Disordered Champion. High-density liquid water represents the triumph of entropy over order, the state where thermal energy and pressure overwhelm the geometric preferences of hydrogen bonding. This structural form, abbreviated HDL, dominates at elevated temperatures and pressures where tetrahedral coordination becomes thermodynamically untenable. In HDL regions, molecules adopt distorted, bent, and broken hydrogen bond networks that pack more efficiently than tetrahedral cages. The result is a denser liquid, typically around 1.15 to 1.21 grams per cubic centimeter in its amorphous ice form, roughly 20 to 25% denser than low-density liquid. The fundamental difference between HDL and LDL lies in coordination geometry. While LDL maintains nearly tetrahedral fork coordination with bond angles close to 109.5 degrees, HDL involves distorted coordination with angles ranging from 90 to 130 degrees. Some molecules in HDL retain four neighbors, but with severely bent hydrogen bonds. Others adopt 5 coordination, squeezing an extra neighbor into their coordination shell through weaker, non-optimally aligned interactions. This geometric flexibility allows molecules to occupy less volume per molecule, increasing bulk density. The oxygen-oxygen distance in HDL shows broader distribution than in LDL. The first peak in the radial distribution function remains near 2.85 angstroms, but becomes wider and less pronounced. This indicates that nearest neighbor distances vary more in HDL than LDL. Some hydrogen bonds stretch to 3 angstroms or beyond, weakening significantly. Others compress slightly below the optimal distance. The distribution reflects the disorder inherent to HDL structure, where geometric optimization takes lower priority than efficient packing. More dramatically, HDL exhibits a distinct feature in its radial distribution function that LDL lacks: enhanced probability at around 3 to 3.5 angstroms, corresponding to the first interstitial space. In tetrahedral networks like LDL, this region remains largely empty, representing the hollow space within tetrahedral cages. In HDL, molecules can insert into these interstitial positions, occupying what would be void space in more ordered structures. This interstitial occupation directly increases density by filling volumes that LDL leaves empty. The second coordination shell in HDL, nominally centered near 4.5 angstroms, shows much weaker definition than in LDL. The second peak in the radial distribution function becomes shallow and broad, indicating that second neighbor positions are poorly defined. Beyond the first shell, HDL rapidly loses structural correlation. The correlation length drops to approximately 5 to 6 angstroms, encompassing only 4 to 8 molecules. This short-range order contrasts sharply with LDL's 11 angstrom correlations. HDL resembles a typical simple liquid where only nearest neighbors show significant positional correlation. The angular distribution of neighbors in HDL reflects the geometric distortions. Rather than clustering sharply around 109.5 degrees as in LDL, the oxygen-oxygen-oxygen angles spread broadly between 80 and 140 degrees. Many molecules show angles closer to 90 degrees, indicating collapsed structures where neighbors approach from more equatorial directions rather than maintaining tetrahedral separation. These distorted geometries reduce hydrogen bond strength because the donor hydrogen no longer points directly toward the acceptor oxygen lone pair. Hydrogen bond strength in HDl averages approximately 18 to 20 kilojoules per mole, noticeably weaker than the 23 to 25 kilojoules per mole typical of LDL. This reduction stems from non-optimal geometries that decrease electrostatic overlap. Additionally, the average coordination in HDl can exceed 4 when counting all hydrogen bonds, including weak or partial bonds. Some molecules maintain 4 strong bonds, but distorted. Others have 3 strong bonds, plus 1 or 2 weaker interactions. This variability makes defining exact coordination numbers ambiguous, but estimates suggest averages around 4.5 to 5. The increased coordination might seem to imply stronger total bonding, but this is misleading. While HDl molecules interact with more neighbors, each individual interaction is weaker. The total binding energy per molecule in HDl is actually similar to or slightly less than in LDL. The difference is that HDl distributes its interactions over more bonds, none of which achieve the optimal strength that LDL's tetrahedral bonds attain. HDl sacrifices bond quality for quantity, a strategy that favors entropy through increased configurational possibilities. Entropy strongly favors HDl at elevated temperatures. The distorted, variable geometries of HDl allow many more molecular configurations than LDL's rigid tetrahedral constraints. Entropy measures the logarithm of accessible configurations, so more configurations mean higher entropy. At high temperatures, where the free energy equals enthalpy minus temperature times entropy, the entropy term grows large. HDl's entropic advantage eventually outweighs LDL's enthalpic advantage from stronger bonding. The crossover temperature depends on pressure, but occurs around 220 Kelvin at atmospheric pressure, according to simulations. Pressure shifts this balance dramatically in HDl's favor. Because HDl occupies approximately 20% less volume than LDL, applying pressure lowers HDl's free energy relative to LDL's. The free energy includes a pressure-volume term, so systems under high pressure minimize volume to reduce this contribution. HDl's compact packing makes it the low free energy state at elevated pressures, even when temperatures are low enough that enthalpy would otherwise favor LDL. This explains why HDl dominates under high-pressure conditions, while LDL thrives at low pressures. Creating pure HDl experimentally requires applying pressure. The standard method involves compressing ordinary or low-density amorphous ice to pressures above approximately 1.6 gigapascals, 16,000 atmospheres, at temperatures below 140 Kelvin. This pressure-induced amorphization transforms low-density ice, or LDA, into high-density amorphous ice, abbreviated HDA. The transformation is dramatic and visible to the naked eye. The sample shrinks noticeably as molecules collapse into denser packing. X-ray diffraction patterns change correspondingly, with peaks shifting to higher angles reflecting shorter intermolecular distances. HDA represents glassy HDl, frozen below the glass transition temperature so molecules cannot rearrange or crystallize. Characterizing HDA provides insight into HDl structure. Neutron diffraction studies reveal that HDA has an average oxygen-oxygen distance of approximately 2.8 angstroms in the first coordination shell, shorter than LDA's 2.75 angstroms. The coordination number increases to approximately 4.7 to 5.2, confirmed through analysis of diffraction patterns and computer simulations. The broader angular distribution and enhanced interstitial occupation distinguish HDA from LDA structurally. Warming HDA above its glass transition temperature near 130 Kelvin transforms it into liquid HDl. This ultraviscous liquid flows slowly, taking minutes or hours to relax mechanical stresses. Continued warming eventually leads to crystallization into high-pressure ice polymorphs like ice IV or ice XII, depending on exact conditions. However, for brief periods during warming, liquid HDl exists in a metastable state that can be probed spectroscopically. These experiments confirm that HDL has properties consistent with simulations: high density, disordered hydrogen bonding, and short structural correlations. Recent experiments have accessed HDL more directly through rapid heating and decompression cycles. In the landmark 2020 study published in Science, Kyung Hwan Kim and colleagues at Stanford University's SLAC National Accelerator Laboratory prepared bulk samples of HDL by isochoric heating of HDA. They used infrared laser pulses to heat thin films of HDA from 160 Kelvin to 205 Kelvin in less than 1 nanosecond. The ultrafast heating preserved the sample density because thermal expansion could not occur on such short timescales. The result was HDL at elevated pressure, estimated at 2,500 to 3,500 bars. The SLAC experiments captured HDL in action using femtosecond X-ray pulses from the LINAC coherent light source. By varying the delay between the infrared heating pulse and the X-ray probe pulse, researchers mapped the time evolution of water's structure during decompression. At early times, less than 10 nanoseconds after heating, the X-ray scattering pattern matched HDL predictions with broad peaks and enhanced interstitial occupation. This provided direct experimental confirmation that HDL exists as a distinct liquid phase, not merely a theoretical concept. The dynamical properties of HDL differ from LDL in ways that reflect the structural differences. HDL exhibits lower viscosity than LDL at the same temperature because its disordered structure flows more easily. Tetrahedral networks in LDL must break multiple strong bonds simultaneously for molecules to rearrange, creating high resistance to flow. HDL's weaker, more variable bonding allows individual molecules to slip past neighbors more readily. Self-diffusion coefficients in HDL are correspondingly higher, estimated at roughly 2 to 3 times the LDL value at equal temperatures. The dielectric properties of HDL also diverge from LDL. HDL has a lower dielectric constant because its collapsed structure restricts molecular reorientations. In densely packed environments, molecules have less freedom to rotate their dipoles in response to electric fields, reducing polarizability. This difference is subtle, perhaps 10 to 20%, but spectroscopic measurements on HDA versus LDA confirm the trend. HDL screens electric fields less effectively than LDL, a counterintuitive result since one might expect the higher density to enhance screening. Spectroscopically, HDL appears distinct from LDL. Raman spectra of HDL show a broader redshifted oxygen-hydrogen stretching band centered near 3,400 wave numbers, reflecting the weaker and more variable hydrogen bonding compared to LDL's 3,200 wave number peak. Infrared absorption similarly reveals the disordered bonding through broad features, lacking the sharp structure characteristic of more ordered environments. X-ray absorption spectroscopy, which probes electronic structure, shows that HDL has enhanced pre-edge features corresponding to weakly bonded or broken hydrogen bonds. The compressibility of HDL provides another distinguishing property. HDL is less compressible than LDL because it already packs efficiently. Applying pressure to HDL cannot significantly reduce volume without forcing molecules into unfavorable close contacts that incur large energetic penalties. LDL, with its open cages and voids, can compress more readily as the tetrahedral structure collapses. This difference in compressibility contributes to the overall compressibility anomaly of water. At low temperatures where LDL dominates, water is relatively compressible. At high temperatures where HDL dominates, water is less compressible. The thermal expansivity of HDL follows normal liquid behavior, increasing with temperature. As HDL warms, molecules gain kinetic energy and push neighbors farther apart on average, causing expansion. This contrasts with LDL, where thermal expansion is small or even negative in some temperature ranges due to structural rearrangements that increase packing efficiency even as thermal motion increases. At temperatures and pressures where HDL dominates, water behaves like a normal liquid, exhibiting all the expected temperature and pressure dependencies without anomalies. The heat capacity of HDL also follows conventional trends, decreasing slowly with increasing temperature as expected from classical thermodynamics. The unusual heat capacity maximum in supercooled water arises when HDL and LDL populations are both significant and interconverting. Pure HDL, like pure LDL, shows unremarkable heat capacity behavior. The anomaly emerges from the mixture, specifically from the energy required to convert between structural forms as temperature changes. HDL itself is not anomalous. It is the transition between HDL and LDL that creates strange behavior. Topologically, HDL networks display entanglement that LDL lacks. Recent analyses using knot theory revealed that hydrogen bond networks in HDL contain trephine knots and other topologically non-trivial structures where loops of bonded molecules thread through each other. LDL networks consist primarily of unknots and simple links with minimal entanglement. This topological distinction provides a fundamental way to characterize the LDL-HDL transition. The transition represents not just a change in local geometry, but a global topological rearrangement from unentangled to entangled networks. Understanding HDL as a thermodynamic state requires appreciating its role as the entropically favored form of water. At high temperatures, maximizing entropy becomes the thermodynamic priority. HDL achieves this through structural disorder that multiplies accessible configurations. At high pressures, minimizing volume becomes the priority. HDL achieves this through efficient packing that eliminates wasted space. In both cases, HDL wins by abandoning the geometric perfection that hydrogen bonding prefers, accepting weaker interactions in exchange for greater flexibility. The HDL state represents water's surrender to chaos, the acknowledgement that perfect tetrahedral order cannot be maintained when thermal energy and pressure become too extreme. It is the disordered champion in the two-liquid war, thriving in harsh environments where the structured warrior falters. Together, these two states engage in continuous battle throughout liquid water, with their relative populations shifting as conditions change. The boundary where these populations balance represents one of the most fascinating transitions in nature, the liquid-liquid phase transition that determines much of water's character. Chapter 6. The liquid-liquid phase transition. The liquid-liquid phase transition in water represents one of the most controversial and intensely studied phenomena in modern physical chemistry. This transition proposes that water can exist as two distinct liquid phases with different densities and structures, separated by a first-order phase boundary similar to the boundary between ice and liquid water. Below a critical point, low-density liquid and high-density liquid can coexist as separate phases with a sharp interface between them. The transition occurs without molecules leaving the liquid state, a purely structural rearrangement rather than a change from liquid to solid or gas. The theoretical foundation for this liquid-liquid phase transition emerged from computer simulations in the late 1980s and early 1990s. Peter Poole, Francesco Sciortino, Ulrich Essmann, and H. Eugene Stanley used the SD2 water model, a simplified representation of water molecules as point particles with directional interactions. Their simulations at low temperatures and varying pressures revealed unexpected behavior. At certain pressures, the density jumped discontinuously as temperature changed, suggesting a first-order phase transition between two distinct liquid forms. Further analysis revealed that these two liquid forms corresponded to low-density liquid with tetrahedral structure and high-density liquid with distorted structure, exactly matching earlier qualitative proposals. The simulations showed that below a critical temperature of approximately 260 Kelvin and critical pressure of 167 megapascals in the SD2 model, LDL and HDL could phase separate. Above this critical point, water transitioned continuously between LDL-like and HDL-like structures without discontinuity. The critical point represented the highest temperature where distinct phases exist. The liquid-liquid critical point, abbreviated LLCP, became the focus of intense interest and controversy. If real water possesses an LLCP, it would profoundly impact understanding of water's anomalies. The strange behaviors of water could be interpreted as arising from proximity to this critical point, where density fluctuations diverge and thermodynamic response functions become anomalously large. This critical point scenario offered a unified explanation for numerous mysteries that had puzzled scientists for over a century. However, the LLCP in simulations occurred deep within no man's land, the temperature region between approximately 150 and 230 Kelvin, where crystallization inevitably occurs in bulk samples. Experimental verification seemed impossible because samples crystallize before reaching the transition. This inaccessibility fueled skepticism. Some scientists argued that the simulated LLCP was an artifact of oversimplified water models that did not accurately represent real water's behavior. Alternative explanations for water's anomalies, not requiring an LLCP, remained competitive. The location of the LLCP depends on which molecular model is used for simulations. Different models with varying accuracy place the critical point at different temperatures and pressures. The SD2 model overestimates the critical temperature by about 40 Kelvin compared to more accurate models. The TIP4P/2005 model, widely regarded as one of the best classical water models, predicts an LLCP near 193 Kelvin and 50 megapascals. The MBPOL model, which includes many body effects and achieves near-quantum accuracy, suggests 198 Kelvin and 125 megapascals. The variation in predicted LLCP locations spans about 50 Kelvin in temperature and 100 megapascals in pressure across different models. This uncertainty complicates experimental searches because researchers do not know exactly where to look. However, all reasonably accurate models agree that an LLCP exists somewhere in the range of 180 to 220 Kelvin and 50 to 200 megapascals. The qualitative conclusion that water has a liquid-liquid transition appears robust even if quantitative details vary. The 2013 breakthrough by Limmer and Chandler using advanced computational techniques provided strong theoretical support. They showed that the free energy landscape of water contains two distinct basins corresponding to LDL and HDL, separated by a barrier. At low temperatures, these basins represent metastable states that can coexist. The barrier height determines the timescale for interconversion. Below the critical temperature, the barrier exceeds thermal energy sufficiently that LDL and HDL domains persist for microseconds or longer before mixing. Above the critical temperature, thermal fluctuations rapidly erase the distinction. Experimental evidence for the liquid-liquid transition accumulated gradually through indirect observations. The anomalous increase in heat capacity, compressibility, and thermal expansion coefficient as water is supercooled all align with predictions from LLCP scenarios. These response functions should diverge as the critical point is approached, producing the observed large values. Extrapolating these trends suggests that a critical point lies somewhere in no man's land, though ice crystallization prevents reaching it directly in bulk samples. The discovery of polyamorphism in amorphous ice provided crucial evidence. In 1985, Osamu Mishima and colleagues demonstrated that compressing hexagonal ice at 77 Kelvin above approximately 1 gigapascal transforms it into HDA. This pressure-induced amorphization creates a new amorphous form distinct from LDA. More remarkably, Mishima showed that HDA can be recovered to ambient pressure, then transforms back to LDA upon heating to approximately 115 Kelvin. This reversible transformation between two amorphous forms suggested that liquid water might also possess two forms related to LDA and HDA. The connection between amorphous ices and liquid phases became clearer as researchers mapped the transformation kinetics. Heating HDA allows it to transform to LDA before crystallizing, implying that molecules can rearrange between the two structural types. If the transformation occurs via a liquid intermediate, this would indicate a liquid-liquid transition. Experiments using calorimetry detected exothermic heat release during the HDA to LDA transformation, consistent with a first-order phase transition. The magnitude and sharpness of the transition resembled expectations for crossing a liquid-liquid phase boundary. The most direct experimental evidence came from the 2020 study by Kim and colleagues at SLAC. Their approach cleverly circumvented crystallization by working on ultra-fast timescales. They heated HDA films to 205 Kelvin in less than 1 nanosecond using infrared laser pulses. This created HDL at elevated pressure before crystallization could nucleate. The sample then expanded and decompressed as the absorbed energy converted to pressure-volume work. Femtosecond X-ray pulses captured snapshots of the structure at different times during this expansion. The X-ray scattering patterns revealed a dramatic transformation. Initially, immediately after heating, the patterns matched HDL with broad peaks in short-range order. At approximately 16 nanoseconds after heating, a shoulder appeared in the scattering pattern at Q equals 1.7 inverse angstroms, matching the characteristic signature of LDL. Over the following microseconds, this LDL feature grew stronger, while the HDL features weakened. The transformation occurred discontinuously rather than gradually, with distinct HDL and LDL domains coexisting during the transition. Critically, the transformation timescale was much faster than crystallization. Ice nucleation and growth require 3 to 50 microseconds at 205 Kelvin. The LDL formation occurred in 20 nanoseconds to 3 microseconds, more than an order of magnitude faster. This temporal separation proved that the structural change represented a liquid-liquid transition rather than partial crystallization. The HDL was transforming into LDL before ice had time to form. Computer simulations using the ST2 model reproduced this behavior, showing rapid density decrease during decompression consistent with crossing a liquid-liquid phase boundary. The discontinuous nature of the transformation provided the strongest evidence for a first-order transition. First-order transitions involve latent heat and occur at fixed temperature and pressure, with properties jumping discontinuously as the system converts from one phase to another. Second-order or continuous transitions show smooth, gradual changes. The appearance of distinct LDL domains growing within HDL matrix indicated phase coexistence, the hallmark of first-order transitions. This observation aligned perfectly with theoretical predictions for a liquid-liquid transition below the critical point. The LLCP scenario predicts specific behaviors near the critical point that can be tested. Approaching the critical point from above, the correlation length should diverge, meaning density fluctuations occur over increasingly large spatial scales. These fluctuations should be detectable through small-angle X-ray scattering, which probes structures larger than typical molecular dimensions. Several experimental groups have reported enhanced SAXS intensity in supercooled water consistent with growing correlation lengths, though interpretation remains debated. The Widom line provides another experimental signature. The Widom line is the locus of maximum correlation length extending from the critical point into the one-phase region above the critical temperature. Crossing the Widom line produces sharp but continuous changes in properties, resembling a phase transition but without actual phase separation. Water's anomalies are most pronounced along trajectories that cross the Widom line, supporting the LLCP hypothesis. The line likely extends from the critical point, around 198 Kelvin upward, toward higher temperatures at appropriate pressures. Alternative scenarios remain under discussion. The stability limit conjecture proposes that water's anomalies arise from approaching a spinodal line where the liquid becomes unstable without requiring a second liquid phase. The critical point-free scenario suggests that water is inherently heterogeneous with coexisting structures but no true phase transition. These alternatives can explain some observations but struggle with others, particularly the discontinuous structural changes seen in ultra-fast experiments. The liquid-liquid transition scenario currently enjoys the strongest support from both simulations and experiments. The topology of the liquid-liquid transition provides deep insight. Recent work using knot theory showed that LDL networks are topologically unentangled, while HDL networks are entangled. The transition between these states requires global rearrangement of hydrogen bonding patterns, threading and unthreading molecular loops through each other. This topological distinction cannot change gradually. A network is either knotted or unknotted. There is no intermediate state. This suggests that the transition must be discontinuous at some level, supporting the first-order nature. Understanding the liquid-liquid transition requires recognizing that it occurs within a narrow region of phase space. At atmospheric pressure, water is too hot for the transition to occur without crystallization. At pressures above roughly 200 megapascals, HDL becomes so overwhelmingly favored that LDL cannot exist. The transition is accessible only in a window of conditions that happens to lie in no man's land. This unfortunate coincidence explains why the phenomenon remained hidden for so long and why experimental confirmation proved so difficult. The implications of the liquid-liquid transition extend far beyond academic interest. Water's anomalous properties arise from the competition between LDL and HDL populations. The density maximum, compressibility minimum, heat capacity maximum, and viscosity anomalies all reflect this structural battle. At temperatures and pressures where LDL dominates, water behaves strangely. Where HDL dominates, behavior normalizes. The transition region, where populations balance, produces the most extreme anomalies as the system's response to perturbations amplifies. The liquid-liquid transition represents the climax of the two-liquid war. Below the critical point, the war reaches stalemate with phase separation into LDL and HDL domains. Above the critical point, the war continues, but without clear winner, with local regions constantly shifting between structural types. This transition determines the fundamental character of water as a substance that refuses to behave like normal liquids, instead maintaining structural complexity that manifests as anomalous properties. Understanding this transition requires examining the broader landscape of supercooled water and amorphous ices where these phenomena become accessible. Chapter 7: Supercooled Water and the Glass Transition. Supercooling water means cooling it below its normal freezing point of 273 Kelvin without allowing ice crystallization to occur. This metastable state is surprisingly common. Pure water droplets in clouds routinely supercool to temperatures around 250 Kelvin before freezing. Under laboratory conditions, with careful purification and containerless techniques, water can be supercooled to approximately 235 Kelvin at atmospheric pressure. Below this temperature, homogeneous ice nucleation becomes so rapid that crystallization occurs within microseconds, regardless of sample purity or technique. This threshold is called the homogeneous nucleation temperature. The region between the homogeneous nucleation temperature at 232 Kelvin and the crystallization onset temperature around 160 Kelvin has earned the ominous nickname no man's land. In this temperature range, water molecules retain sufficient mobility to rearrange into ice crystals, while thermodynamic driving forces for crystallization become overwhelming. Any bulk sample of liquid water that enters no man's land crystallizes almost instantly, typically within tens to hundreds of microseconds. This rapid crystallization prevented experimental studies of liquid water in no man's land for decades, leaving a critical gap in knowledge exactly where the most interesting phenomena were predicted to occur. The liquid-liquid critical point, if it exists, lies somewhere in no man's land. Theoretical predictions place it between 180 and 220 Kelvin, depending on which computational model is consulted. The inaccessibility of this region created a frustrating situation where the most important temperature range for understanding water's anomalies remained experimentally forbidden. Scientists developed ingenious workarounds, but each approach faced limitations that complicated interpretation. One strategy involves studying water in confined geometries where crystallization can be suppressed. When water is trapped in nanopores smaller than the critical nucleus size for ice formation, crystallization becomes kinetically hindered. Researchers used mesoporous silica materials with pore diameters of 1 to 3 nanometers, filling them with water and cooling to temperatures well below the homogeneous nucleation point. Confined water in these systems can persist as liquid down to approximately 160 to 180 Kelvin, depending on pore size and surface chemistry. Calorimetric measurements on confined water reveal fascinating behavior. As temperature decreases, the heat capacity increases dramatically, reaching values several times higher than normal liquid water. This rise is consistent with approaching a critical point where thermodynamic response functions diverge. Dielectric measurements show similarly anomalous behavior, with relaxation times increasing much faster than expected from simple homogeneous temperature dependence. The data suggest a fragile to strong transition near 220 Kelvin, where water's dynamics shift from fragile liquid behavior with superhomogeneous temperature dependence to strong liquid behavior with homogeneous dependence. However, confinement complicates interpretation. The confining surfaces interact with water molecules, potentially altering structure and dynamics. Water near hydrophilic silica surfaces forms ordered layers extending several molecular diameters from the interface. These surface effects might dominate the signal in nanopores, where most molecules are within a few nanometers of a wall. Distinguishing between genuine bulk water properties and confinement artifacts requires careful controls and multiple pore sizes. Despite these complications, confined water studies provided valuable evidence that water's anomalous behavior intensifies as no man's land is approached. Another approach involves emulsifying water into tiny droplets suspended in oil. Small droplets have reduced probability of containing ice nucleating impurities, allowing deeper supercooling than bulk samples. Droplets with diameters of 1 to 10 micrometers can be cooled to around 230 Kelvin before freezing, slightly extending the accessible temperature range. X-ray diffraction measurements on supercooled droplets revealed smooth evolution of structural features down to 227 Kelvin, showing increasing correlation lengths consistent with approaching a critical point. Below 227 Kelvin, crystallization prevented further measurements. The glass transition offers another window into deeply supercooled water properties. All liquids can form glasses if cooled rapidly enough to avoid crystallization. The glass transition occurs when molecular motion becomes so slow that the liquid cannot relax structural rearrangements on experimental timescales. Below the glass transition temperature, the material behaves as a solid glass rather than a supercooled liquid, even though no crystallization has occurred. The glass represents a frozen snapshot of the liquid structure at the temperature where molecular motion arrested. For water, forming bulk glass through direct cooling requires extraordinary cooling rates exceeding 1 million Kelvin per second. This hyperquenching bypasses the temperature range where crystallization is fastest, preserving the liquid in amorphous form. Early experiments by researchers including Bruggeler and Mayer in 1980 achieved vitrification by depositing thin water films onto copper substrates cooled to 77 Kelvin. The resulting material, low-density amorphous ice, showed no crystalline diffraction peaks, confirming its glassy nature. The glass transition temperature of low-density amorphous ice has been debated for decades. Early calorimetry experiments identified a weak step in heat capacity near 136 Kelvin, interpreted as the glass transition. Heating hyperquenched glassy water through this temperature appeared to restore liquid-like behavior before crystallization intervened at 150 to 160 Kelvin. This suggested a glass transition at 136 Kelvin, corresponding to liquid water at that temperature having relaxation times around 100 seconds, the conventional definition of vitrification. More recent work complicates this picture. Careful calorimetry studies using different heating rates and annealing protocols revealed that the feature at 136 Kelvin is better interpreted as a shadow glass transition or annealing prepeak rather than the true glass transition. Shadow glass transitions occur in various glassy materials when low-temperature agging creates excess enthalpy that releases upon heating, creating endothermic peaks that mimic glass transitions but lack the characteristic features like frequency-dependent relaxation times. Advanced measurements using fast scanning calorimetry, which can heat samples at rates up to 1 million Kelvin per second, combined with dielectric spectroscopy probing molecular relaxation times, converge on a higher glass transition temperature. For confined water in mesoporous silica, multiple techniques consistently identify glass transitions between 170 and 200 Kelvin, depending on confinement size. Bulk water's glass transition likely lies near the upper end of this range, around 190 to 200 Kelvin, though crystallization prevents direct measurement. This revised glass transition temperature places it deep within no man's land, overlapping with predicted liquid-liquid critical point locations. The coincidence is suggestive. Some theories propose that the apparent fragile-to-strong transition in supercooled water dynamics actually represents approaching the glass transition of the low-density liquid component. As temperature decreases, the liquid becomes increasingly dominated by LDL, which has higher viscosity and slower dynamics than HDL. The crossover to Arrhenius behavior would then reflect the system becoming kinetically trapped in LDL-dominated configurations. The relationship between amorphous ices and supercooled liquid water provides crucial insights. Low-density amorphous ice represents frozen LDL, preserving its tetrahedral structure in glassy form. Heating LDA above its glass transition creates supercooled liquid water with high LDL content. This liquid exists only briefly before crystallizing, but during that interval, it exhibits properties consistent with theoretical predictions for LDL-dominated water. Viscosity is high, several orders of magnitude above normal water at 0 Celsius. Density is low, approximately 0.94 grams per cubic centimeter. High-density amorphous ice represents frozen HDL, with distorted hydrogen bonding and collapsed structure. HDA forms through several routes. The most common involves compressing hexagonal ice at temperatures around 77 Kelvin to pressures exceeding 1.6 gigapascals. The pressure overcomes energy barriers, preventing structural transformation, forcing molecules from tetrahedral to collapsed configurations. The transformation is dramatic, with volume decreasing by roughly 20%. Alternatively, HDA forms by compressing LDA above approximately 0.6 of a gigapascal at similar temperatures. The HDA to LDA transformation upon decompression and gentle heating provides strong evidence for a liquid-liquid transition. When HDA is decompressed to ambient pressure and slowly warmed, it transforms to LDA at approximately 127 Kelvin. Calorimetry measurements detect exothermic heat release during this transformation, indicating a first-order phase transition. The sharpness and reproducibility of the transformation suggest it occurs via a liquid intermediate. The sample briefly becomes liquid HDL, which then transforms to liquid LDL before solidifying again below the glass transition temperature. Very high-density amorphous ice, abbreviated VHDA, represents an even more collapsed form discovered by Thomas Lowerting and colleagues. VHDA forms when HDA is annealed at elevated pressure and temperature, allowing further structural relaxation and densification. The density reaches approximately 1.26 grams per cubic centimeter, about 30% higher than LDA and 10% higher than initial HDA. Neutron diffraction reveals that VHDA achieves extreme packing through doubled occupancy of interstitial sites, with molecules squeezing into regions that remain void in LDA and partially filled in HDA. The existence of multiple amorphous forms with distinct densities strongly supports the idea that liquid water also possesses multiple structural states. If glassy water can exist in qualitatively different forms depending on preparation conditions, it follows that liquid water should exhibit similar structural diversity. The amorphous ices provide frozen snapshots of the structures that would exist in deeply supercooled liquid water at corresponding conditions. LDA reveals LDL structure, HDA reveals HDL structure, and the transformations between them mirror liquid-liquid transitions. Recent experimental breakthroughs penetrated no man's land directly using ultra-fast techniques. Greg Kimmel and Bruce Kay at Pacific Northwest National Laboratory developed a method to study water in no man's land by using pulsed heating. They deposited crystalline ice films onto cold substrates, then briefly heated the surface with infrared laser pulses lasting microseconds. The heating melted the topmost layer into liquid water for a fraction of the crystallization time. Before crystallization could complete, the pulse ended and the sample cooled back below the melting point, quenching the partially crystallized liquid. By repeating this pulse-melt-quench cycle thousands of times and carefully controlling pulse energy and duration, Kimmel and Kay could keep samples partially liquid in no man's land long enough to perform measurements. Infrared spectroscopy during the liquid phase revealed hydrogen bonding characteristics and structural evolution. The results showed that water in no man's land exhibits strong tetrahedral ordering with spectral features resembling LDA more than normal liquid water. This confirmed that LDL populations dominate at these low temperatures. Another breakthrough came from electron diffraction studies by Yuhan Huang and colleagues. They developed techniques to cool micrometer-sized water droplets through no man's land while capturing electron diffraction patterns on nanosecond timescales. The key insight was cooling droplets from below rather than above. By starting with amorphous ice at low temperature, rapidly heating it into no man's land, capturing diffraction patterns, then cooling it back before crystallization completed, they obtained structural information without allowing sufficient time for ice nuclei to grow. The electron diffraction patterns revealed continuous evolution of structural features through no man's land. At low temperatures near 160 Kelvin, the structure resembled LDA with pronounced tetrahedral order. As temperature increased toward 210 Kelvin, the structure evolved toward higher density with weaker tetrahedral signatures. The smooth progression suggested that water transforms continuously from LDL-dominated to HDL-dominated structure as temperature rises, consistent with crossing above the liquid-liquid critical point where no sharp phase boundary exists. The isothermal compressibility of water, which measures volume change in response to pressure, exhibits a minimum at approximately 46 degrees Celsius at atmospheric pressure. As water is cooled below this temperature, compressibility increases, slowly at first, then more rapidly as temperature drops. Supercooling studies show that compressibility continues rising dramatically, apparently diverging as no man's land is approached. This divergence is characteristic of approaching a critical point where density fluctuations become infinite in range. Similarly, the heat capacity at constant pressure increases strongly upon supercooling, reaching values more than twice the normal liquid value by 230 Kelvin. Extrapolations suggest the heat capacity would diverge near 220 Kelvin if crystallization could be avoided. The thermal expansion coefficient also grows rapidly in magnitude and negative values, meaning water contracts when heated in certain supercooled regimes. All these anomalous thermodynamic behaviors align with predictions from liquid-liquid critical point scenarios. The Speedy Angel scenario, proposed in the 1970s, suggested that supercooled water might encounter a stability limit or spinodal line where the liquid becomes thermodynamically unstable. Compressibility and other response functions would diverge at this spinodal, producing apparent critical behavior. Later work showed that a liquid-liquid critical point located slightly above the spinodal could produce similar phenomenology while avoiding the unphysical implication of absolute instability. The modern interpretation favors the critical point over the pure spinodal scenario, though distinguishing between them remains challenging. Understanding supercooled water and the glass transition requires recognizing that no man's land is not a forbidden zone, but rather a region where crystallization kinetics dominate. The liquid state itself remains thermodynamically accessible. It is simply that the pathway to crystalline ice becomes overwhelmingly fast. By using techniques that work faster than crystallization, researchers have begun mapping this crucial region. The picture emerging confirms theoretical predictions. Water transitions from LDL-dominated structure at low temperatures to HDL-dominated structure at higher temperatures, with the transition region producing the anomalous properties that make water unique. Observing this transition directly required experimental techniques that could see water's structure changing in real time. Chapter 8: Experimental Evidence from X-ray Scattering. X-ray scattering provides the most direct method for determining liquid structure at the molecular level. When X-rays pass through water, they interact with electrons surrounding each atom. The scattered X-rays interfere constructively or destructively depending on the relative positions of atoms, creating diffraction patterns that encode structural information. For crystalline materials, sharp diffraction spots reveal the periodic lattice. For liquids, diffuse rings indicate the statistical distribution of interatomic distances without long-range periodicity. Analyzing these diffraction patterns allows reconstruction of the radial distribution function that describes how molecular density varies with distance from any reference molecule. The oxygen-oxygen radial distribution function obtained from X-ray scattering of water at room temperature shows a prominent first peak centered at approximately 2.85 angstroms, corresponding to the typical distance between hydrogen-bonded neighbors. A broader second peak appears near 4.5 angstroms, indicating second shell neighbors. Beyond about 8 angstroms, the function oscillates weakly around unity, reflecting the loss of positional correlation at larger distances. These features reveal that liquid water maintains significant local structure extending through 2 to 3 coordination shells, unlike simple liquids where only nearest neighbors show correlation. Temperature-dependent X-ray scattering studies reveal how water's structure evolves as conditions change. As water is heated from 0 to 100 Celsius, the first peak in the radial distribution function becomes broader and shifts slightly to larger distances, indicating thermal expansion and increasing structural disorder. The second peak diminishes in amplitude, showing that longer-range correlations weaken. The coordination number derived from integrating the first peak increases from approximately 4.3 at 0 Celsius to 4.8 at 100 Celsius, reflecting the shift from tetrahedral toward more collapsed coordination. Wide-angle X-ray scattering, abbreviated WAXS, probes length scales of a few angstroms, perfect for resolving nearest neighbor and second neighbor correlations. The scattering vector Q, which describes the angular dependence of scattered intensity, ranges from approximately 1 to 10 inverse angstroms in typical WAXS experiments. The first peak in the structure factor, S of Q, which represents the Fourier transform of the radial distribution function, appears near 2 inverse angstroms. Additional peaks at higher Q values provide details about molecular orientations and hydrogen bonding geometry. Small-angle X-ray scattering, abbreviated SAXS, probes much larger length scales from approximately 10 to several hundred angstroms. SAXS uses very small scattering angles where only long-range density fluctuations contribute to the signal. For homogeneous liquids, SAXS intensity at small q should approach the value determined by isothermal compressibility, reflecting thermodynamic density fluctuations. Any deviation from this expectation indicates structural heterogeneity on nanometer scales, suggesting that the liquid contains regions with different densities or compositions. In 2010, Chung Huang and colleagues published controversial SAXS measurements on ambient water that claimed to detect nanometer-scale density fluctuations consistent with LDL and HDL domains coexisting at room temperature. Their data showed excess scattering intensity at small angles that they interpreted as arising from scattering contrast between low-density and high-density regions. They estimated the characteristic size of these heterogeneous domains as approximately 1 to 2 nanometers, containing 10 to 30 molecules. This would imply that the two-state character of water persists even at room temperature, not just in the supercooled regime. The Huang paper sparked intense debate. Critics argued that the observed SA-XS features could be explained by ordinary thermodynamic density fluctuations in a homogeneous liquid without requiring structural heterogeneity. They performed computer simulations using water models like TIP4PU that reproduce bulk properties accurately and calculated the expected SA-XS intensity. These simulations showed the same small-angle upturn that Huang observed, but the simulations contained no structural heterogeneity by construction. The SA-XS signal arose purely from statistical fluctuations in a uniform liquid. Subsequent SA-XS studies using different X-ray sources and analysis methods produced conflicting results. Some groups confirmed the excess scattering and interpreted it as evidence for heterogeneity. Others found results consistent with homogeneous liquid predictions. The disagreement hinged partly on experimental challenges. SA-XS measurements on pure liquids are notoriously difficult because the signals are weak and sensitive to systematic errors like parasitic scattering from sample containers, capillary walls, and residual air scattering. Subtracting these backgrounds accurately requires exquisite control. The debate about ambient water heterogeneity remains unresolved, but consensus has emerged that any heterogeneity at room temperature must be transient and limited to nanometer scales. Unlike deeply supercooled water, where LDL and HDL might phase separate into macroscopic domains, ambient water shows at most flickering nanoscale fluctuations, where small clusters of molecules transiently adopt LDL-like or HDL-like configurations before thermal motion erases them. The practical significance is that ambient water behaves as a homogeneous liquid for most purposes, with heterogeneity appearing only when probed on picosecond timescales and nanometer-length scales. X-ray absorption spectroscopy, abbreviated XAS, provides complementary structural information by probing the local electronic environment around specific atoms. In XAS measurements, X-ray photon energy is scanned across an absorption edge where core electrons are excited to unoccupied states. The absorption spectrum depends sensitively on the number and geometry of neighboring atoms because scattering of the excited electron from nearby atoms creates interference patterns in the absorption probability. Analyzing these patterns reveals coordination numbers, bond distances, and bond angles. For water, oxygen K-edge XAS near 540 electron volts proved particularly informative. The pre-edge region of the spectrum shows features corresponding to transitions into antibonding orbitals. The intensity and position of these features depend on hydrogen bonding strength and geometry. Weakly hydrogen-bonded or broken bonds produce enhanced pre-edge intensity because the antibonding orbitals lie lower in energy and are more accessible. Strongly hydrogen-bonded water shows suppressed pre-edge features because strong bonds push the antibonding orbitals to higher energy. Anders Nilsson and colleagues at Stockholm University pioneered use of XAS to study water structure. Their measurements showed that the oxygen K-edge spectrum could be decomposed into two components, one characteristic of strongly hydrogen-bonded tetrahedral environments resembling ice, and another characteristic of weakly bonded or distorted environments. The relative intensity of these components changed with temperature, with the ice-like component decreasing as water heated. This supported the two-state model, suggesting that populations of LDL-like and HDL-like environments shift with temperature. However, these XAS interpretations also faced controversy. Other research groups argued that the spectral changes could be explained by continuous distortions of hydrogen bonds rather than discrete structural states. The debate involved complex quantum chemistry calculations of how various hydrogen bonding geometries affect electronic structure and absorption spectra. Different theoretical approaches gave somewhat different predictions, making it difficult to conclusively resolve whether the observed spectra required two distinct states or merely showed effects of a broad distribution of bond strengths and angles. X-ray emission spectroscopy, abbreviated XES, provided another probe by measuring the energy of X-rays emitted when core holes created by X-ray absorption are filled by outer electrons. The emission spectrum reflects the occupied electronic states and thus contains information about bonding. Combined XAS and XES measurements allowed mapping of both occupied and unoccupied electronic states, providing a more complete picture of water's electronic structure. The results generally supported significant structural heterogeneity, but could not definitively prove or disprove discrete two-state character. The breakthrough came from time-resolved X-ray scattering using ultra-fast X-ray pulses. Conventional X-ray sources, including synchrotrons, produce continuous or quasi-continuous X-ray beams. Measurements represent time-averaged snapshots over milliseconds or longer. Any dynamical processes faster than the measurement time appear blurred. Water's hydrogen bond dynamics occur on femtosecond to picosecond timescales, far faster than conventional sources can resolve. Observing these dynamics required X-ray sources capable of producing femtosecond pulses with sufficient intensity to capture diffraction patterns in a single shot. X-ray free electron lasers, abbreviated XFELs, revolutionized ultrafast science by providing exactly these capabilities. The LINAC coherent light source at SLAC National Accelerator Laboratory, which began operations in 2009, produces X-ray pulses as short as 10 femtoseconds, with peak brilliance billions of times higher than synchrotrons. Each pulse contains approximately 10 to the 12th photons, sufficient to obtain diffraction patterns from single molecules or tiny crystals. For liquid samples, a single pulse captures a snapshot of molecular structure frozen at one instant in time. In 2018, Fivos Parakis and colleagues working with Anders Nilsson used femtosecond X-ray scattering at the LCLS to probe water's ultrafast structural dynamics. They measured the diffraction pattern from liquid water after excitation by an infrared laser pulse. The infrared pulse deposits energy into water by exciting molecular vibrations, particularly the oxygen-hydrogen stretching mode. This excitation temporarily disrupts hydrogen bonds in the illuminated volume. By varying the delay between the infrared pump pulse and the X-ray probe pulse, researchers could watch how the structure relaxed after disruption. The results revealed correlated motion on timescales below 100 femtoseconds. When one hydrogen bond broke due to vibrational excitation, neighboring bonds responded almost instantaneously, strengthening to compensate. This cooperative response occurred much faster than individual molecular diffusion, indicating that hydrogen bond networks possess collective modes where many molecules move in concert. The observation confirmed that water should be understood as a network rather than a collection of independent molecules, with structural changes propagating through the network on ultra-fast timescales. Further experiments examined deeply supercooled water using the rapid heating and probing technique. Samples of HDA were heated by infrared pulses to create liquid HDL, then probed with X-ray pulses at various delays. The X-ray scattering patterns showed dramatic evolution over nanoseconds to microseconds. Initially, the patterns matched HDL structure with broad, short-range order. Over tens of nanoseconds, a new peak appeared at low Q values corresponding to developing LDL structure. The two peaks coexisted during the transformation, indicating phase separation rather than uniform structural change throughout the sample. The coexistence of distinct HDL and LDL scattering signatures provided the most direct evidence for two separable liquid forms. If water contained only a continuous distribution of local structures, the scattering pattern would show smooth evolution as the average structure changed. Instead, the appearance of distinct peaks indicated that molecules were partitioning into two populations with qualitatively different structures. Some regions remained HDL-like, while others transformed to LDL-like, with relatively few molecules in intermediate states. This bimodal distribution is exactly what the two-state model predicts. Quantitative analysis of the time-dependent scattering patterns allowed estimation of the LDL volume fraction as the system evolved. Initially, nearly 100% of the sample was HDL. After 20 nanoseconds, approximately 10 to 20% had transformed to LDL. By 3 microseconds, LDL fraction reached 40 to 50%. The transformation continued until crystallization intervened. Fitting the kinetics to models of nucleation and growth provided estimates of the interfacial energy between LDL and HDL domains, confirming that they represent distinct phases with measurable surface tension. Small-angle X-ray scattering during the HDL to LDL transformation revealed additional details about the spatial organization of phases. The SAXS intensity increased strongly as LDL domains nucleated and grew, indicating density contrast between phases. Analyzing the Q-dependence of SAXS using Guinea analysis suggested that LDL domains had characteristic sizes of approximately 50 to 200 nanometers initially, growing larger over time. This size scale far exceeds molecular dimensions, confirming that the transformation involved macroscopic phase separation rather than microscopic structural fluctuations. The pressure dependence of scattering patterns provided another test. By varying the initial HDA compression and heating protocol, researchers accessed different points in temperature-pressure space. At lower pressures around 1,000 to 2,000 bars, the HDL to LDL transformation occurred rapidly and completely. At higher pressures above 3,000 bars, the transformation slowed and became incomplete, with significant HDL fraction remaining even after several microseconds. This pressure dependence matches theoretical predictions for the liquid-liquid phase diagram, where LDL becomes increasingly unfavorable at elevated pressures. X-ray scattering techniques have progressed from simple radial distribution function measurements to sophisticated time-resolved studies capable of capturing structural transformations in real time. These experiments provide the most compelling evidence that water indeed contains two distinct liquid forms that can coexist and interconvert. The scattering patterns reveal not just that structure changes with temperature and pressure, but that it changes through phase separation into distinct domains with different densities and coordination geometries. This observation elevates the two-state model from theoretical hypothesis to experimental reality, confirming that water's internal conflict between tetrahedral and collapsed structures manifests as an actual liquid-liquid phase transition. Chapter 9: The 2020 Femtosecond Breakthrough. November 19, 2020 marked a watershed moment in water science. The journal Science published experimental observation of the liquid-liquid transition in bulk supercooled water under pressure by Kyung-Hwan Kim and colleagues. This paper provided the first direct, unambiguous experimental confirmation that water can exist in two distinct liquid phases separated by a first-order phase boundary. The achievement required combining multiple cutting-edge technologies: ultra-fast lasers, X-ray free electron lasers, cryogenic sample preparation, and sophisticated data analysis. The result resolved decades of debate and fundamentally confirmed theoretical predictions about water's hidden complexity. The experimental challenge was formidable. The liquid-liquid transition was predicted to occur in no man's land, where crystallization happens within microseconds. Any technique attempting to observe the transition needed to work faster than crystallization while still allowing sufficient time for structural rearrangement to occur. Previous approaches using confined water or emulsions provided indirect evidence, but always faced questions about whether confinement effects altered the intrinsic behavior. The breakthrough required studying bulk water, not confined or interfacially dominated samples. Kim and colleagues' solution involved starting from high-density amorphous ice rather than liquid water. They prepared thin films of HDA approximately 200 nanometers thick by vapor deposition onto cryogenically cooled substrates. The thin film geometry was crucial because it allowed rapid, uniform heating throughout the sample volume. Thicker samples would develop temperature gradients that complicated interpretation. The 200 nanometer thickness represented a compromise between being thin enough for uniform heating and thick enough to provide adequate X-ray scattering signal. The samples were maintained at approximately 160 Kelvin and elevated pressure, achieved by sandwiching the HDA film between diamond windows. Diamond is nearly transparent to X-rays while providing excellent mechanical strength to contain high pressures. The pressure in these experiments was estimated at 2,000 to 3,500 bars based on the sample preparation protocol and diamond spacing. This pressure places the system in the region where both HDL and LDL should be thermodynamically accessible, depending on temperature. Heating was accomplished using infrared laser pulses at 1,450 nanometer wavelength, with duration of approximately 1 nanosecond and energy of several millijoules per square centimeter. This wavelength corresponds to overtones of the oxygen-hydrogen stretching vibration in water, providing efficient energy absorption. The nanosecond pulse duration was long enough to allow energy to distribute uniformly throughout the film thickness, but short enough to avoid significant heat dissipation to the surroundings during the pulse. The heating rate exceeded 10 to the 10th Kelvin per second, approximately 1 trillion times faster than typical laboratory heating. This ultra-fast heating created what is called isochoric heating, meaning constant volume heating. During the nanosecond heating pulse, thermal expansion cannot occur because inertia prevents the diamond windows from moving apart on such short timescales. The sample volume remains essentially fixed, while temperature jumps from 160 to approximately 205 Kelvin. This sudden temperature increase at constant density brings the system into a state far from equilibrium. The density matches cold HDA, approximately 1.17 grams per cubic centimeter, but the temperature corresponds to conditions where lower density is thermodynamically favored. Following isochoric heating, the system must evolve toward equilibrium. At 205 Kelvin and 1 atmosphere, equilibrium water has density near 0.98 grams per cubic centimeter, significantly lower than the initial 1.17. The system cannot reach this density instantly because expansion requires mechanical work against the surrounding pressure. As thermal energy converts to mechanical energy, the sample expands and cools slightly. If pressure decreases sufficiently during expansion, the system may cross the liquid-liquid phase boundary, triggering transformation from HDL to LDL. Observing this transformation required capturing X-ray scattering patterns at precisely controlled times after the heating pulse. The team used femtosecond X-ray pulses from the LINAC coherent light source, each pulse containing sufficient photons to record a complete diffraction pattern in a single shot. By varying the delay between the infrared heating pulse and the X-ray probe pulse from nanoseconds to microseconds, they created a stop-motion movie of structural evolution. Each delay time required a fresh sample because the heating and probing process destroyed the sample. Accumulating statistics required thousands of shot repetitions at each delay time. The earliest X-ray patterns, captured within 10 nanoseconds after heating, showed structure characteristic of HDL. The scattering featured a broad peak at Q near 3 inverse angstroms corresponding to nearest neighbor oxygen-oxygen spacing of approximately 2.8 angstroms. The peak width and shape matched computational predictions for HDL, with significant structural disorder and short correlation lengths. Notably, these patterns differed clearly from crystalline ice, which would show sharp Bragg peaks. The sample was liquid HDL, confirming that isochoric heating successfully created liquid rather than merely heated amorphous solid. By 16 nanoseconds after heating, a new feature emerged in the scattering pattern. A shoulder appeared at lower Q near 1.7 inverse angstroms, corresponding to real space distances of approximately 3.7 angstroms. This feature matched the characteristic second neighbor peak expected for tetrahedral LDL structure. In tetrahedral networks, Second shell neighbors occupy positions at approximately the square root of 8 over 3 times the nearest neighbor distance, which for 2.75 angstrom nearest neighbors gives approximately 3.7 angstroms. The appearance of this peak indicated that LDL structure was developing. The timescale of LDL emergence, approximately 16 nanoseconds, is remarkably fast yet clearly distinguishable from the 3 to 50 microsecond crystallization time at these conditions. This temporal separation proved crucial. If the structural changes occurred on microsecond timescales, one could not exclude partial crystallization as the explanation. The nanosecond transformation was too fast for ice nucleation to account for. Ice formation requires molecules to find and lock into crystalline sites, a process limited by diffusion. The observed transformation occurred faster than diffusive processes, indicating a cooperative structural rearrangement throughout the material. Over the following microseconds, the LDL peak grew stronger while the HDL peak weakened. By 3 microseconds after heating, both peaks remained visible with comparable intensities, indicating substantial fractions of both phases coexisting. This coexistence represents the key observation. If water transitioned continuously from HDL to LDL structure, intermediate states would dominate, showing a single broad peak that gradually shifted position. Instead, the distinct peaks indicated bimodal structure distribution, with molecules partitioning into 2 populations. Computer simulations using the SD2 water model reproduced the experimental observations quantitatively. The simulations started from HDA configuration, applied rapid heating to 205 Kelvin, then followed the structural evolution. The simulated scattering patterns showed the same sequence: initial HDL character, emergence of LDL peak at 16 nanoseconds, growth of LDL fraction over microseconds, and eventual crystallization. Agreement between experiment and simulation validated both the experimental interpretation and the water model's accuracy for describing the liquid-liquid transition. Analysis of individual molecules in the simulations revealed the mechanism of transformation. Initially, nearly all molecules occupied collapsed, distorted hydrogen bonding environments characteristic of HDL. As the system expanded and pressure decreased, small clusters of molecules spontaneously reorganized into tetrahedral configurations. These LDL clusters grew by incorporating molecules from the surrounding HDL matrix. The growth was not driven by diffusion of individual molecules, but by cooperative rearrangement, where entire hydrogen bond networks flipped from collapsed to tetrahedral topology. The transformation occurred heterogeneously throughout the sample. LDL nucleated at multiple sites, creating domains that expanded outward. The domain boundaries represented interfaces between LDL and HDL regions where molecules transitioned from one structural type to the other. These interfaces had finite thickness, approximately 1 to 2 nanometers, containing molecules in intermediate configurations. However, most molecules resided in the bulk of LDL or HDL domains with characteristic structures, not in the interface regions. This spatial organization confirmed phase separation. Measurements of density fluctuations using small-angle scattering provided additional evidence. As LDL domains nucleated within HDL matrix, the density contrast created enhanced small-angle scattering intensity. The intensity grew during the transformation, peaking when comparable volumes of both phases existed, then decreased as one phase began dominating. The Q-dependence of small-angle intensity allowed estimation of domain sizes using porod analysis. The results indicated domains of 50 to 200 nanometers initially, growing larger over time as coalescence occurred. The discontinuous nature of the transformation characterized it as first-order phase transition. First-order transitions involve latent heat and occur at fixed temperature and pressure, with properties jumping discontinuously. The appearance of 2 distinct scattering peaks indicated discontinuous density change. Calorimetric measurements on similar samples detected exothermic heat release during HDL to LDL transformation, confirming latent heat. The transformation kinetics followed nucleation and growth, behavior characteristic of first-order transitions, not the smooth, continuous changes expected for second-order or crossover phenomena. The pressure dependence provided crucial validation. By varying the initial HDA compression, the team accessed different pressures. At lower pressures around 1,000 to 1,500 bars, LDL formation occurred earlier and more completely. At higher pressures above 3,000 bars, LDL formation was suppressed, with samples remaining predominantly HDL even after several microseconds. This pressure dependence matches theoretical phase diagrams predicting that LDL becomes unfavorable at elevated pressures due to its lower density. The temperature dependence was constrained by crystallization, which limited how long liquid samples persisted. At 205 Kelvin, crystallization began around 5 to 10 microseconds after heating. At slightly higher temperatures around 215 Kelvin, crystallization was slower, allowing observation times extending to 20 microseconds. However, higher temperatures also reduced the driving force for LDL formation, resulting in smaller LDL fractions. At 225 Kelvin and above, HDL transformed directly to ice without significant LDL formation, suggesting the liquid-liquid phase boundary was crossed. Comparison with amorphous ice transformations strengthened the connection between glassy and liquid phases. The HDA to LDA transformation observed upon heating compressed ices showed similar characteristics: exothermic heat release, discontinuous density change, and pressure-dependent kinetics. The primary difference was that amorphous transformations occurred below the glass transition where molecules were kinetically frozen, while the liquid-liquid transformation occurred above the glass transition where molecules could flow. The structural changes were analogous, supporting the interpretation that LDA represents glassy LDL and HDA represents glassy HDL. The experiments also addressed alternative explanations for water's anomalies. The stability limit conjecture proposed that anomalies arise from approaching a spinodal where the liquid becomes mechanically unstable against density fluctuations. However, spinodals are not associated with phase separation or coexistence. The observation of two distinct structural populations coexisting contradicts pure spinodal scenarios. The critical point-free hypothesis suggested that water contains structural heterogeneity but without a true phase transition. The observation of sharp LDL nucleation and domain growth with measurable interfacial energy contradicts this scenario as well. The implications extended beyond confirming the liquid-liquid transition. The observations demonstrated that the transition occurs on timescales and at conditions where direct experimental access is possible using ultrafast techniques. This opens the door for detailed studies of the transition mechanism, interfacial properties, nucleation kinetics, and connections to water's anomalous thermodynamics. Understanding how and why water transforms between liquid forms provides mechanistic insight into the molecular origins of its unique properties. The success also validated the strategy of using XFELs for studying metastable and transient states of matter. Many materials exhibit phase transitions or structural transformations that occur too quickly for conventional techniques, but are accessible to ultrafast probes. Water represented an ideal test case because of the extensive theoretical predictions and the fundamental importance of the questions. The positive results encouraged application of similar approaches to other materials and phenomena where rapid dynamics prevent conventional study. Critics raised questions about whether the observed transformation truly occurred in the liquid state or might involve transient amorphous phases below the glass transition. However, multiple lines of evidence confirmed liquid character. The diffusion rates inferred from domain growth kinetics were consistent with liquid diffusion coefficients at 205 Kelvin, approximately 10 to the negative 10 square meters per second. If the system were glassy, diffusion would be negligible and structural changes would occur only through slower activated hopping processes. The observed fast, cooperative rearrangements indicated liquid mobility. The 2020 breakthrough resolved the question of whether water's liquid-liquid transition is real. The answer is unequivocally yes. Water can exist as two distinct liquid phases, low-density liquid with tetrahedral structure and high-density liquid with collapsed structure, separated by a first-order phase boundary. This transition occurs in bulk water at experimentally accessible conditions when studied using techniques faster than crystallization. The transformation involves nucleation and growth of one phase within the other, with clear spatial phase separation and measurable interfacial properties. Water's anomalous behaviors arise from the competition between these two forms and from fluctuations near the liquid-liquid critical point. Understanding water requires recognizing its split personality and the warfare between structural states that determines its macroscopic character. Chapter 10: The Anomalies Explained. Water's anomalous properties have puzzled scientists for centuries, appearing as violations of how normal liquids should behave. The density maximum at 4 degrees Celsius, the compressibility minimum at 46 degrees Celsius, the heat capacity increase upon cooling, the viscosity decrease under pressure, and dozens of other peculiarities all seem to require separate, disconnected explanations. The two-state model provides a unified framework that explains virtually all of water's anomalies through a single mechanism: the competition between low-density liquid and high-density liquid populations. Understanding how this competition creates each anomaly reveals the deep connection between molecular structure and macroscopic behavior. The density anomaly represents the most famous of water's peculiarities. Most substances contract steadily as temperature decreases, becoming denser until they freeze. Water follows this pattern only partially. Cooling water from 100 degrees Celsius towards zero causes normal contraction, with density increasing from 0.958 grams per cubic centimeter at 100 degrees to approximately 0.9998 grams per cubic centimeter at 4 degrees Celsius. This represents the density maximum. Below 4 degrees, the trend reverses. Further cooling causes expansion, with density decreasing to 0.99984 grams per cubic centimeter at 0 degrees. Ice at 0 degrees has even lower density at 0.917 grams per cubic centimeter, which is why it floats. The two-state model explains this reversal through structural populations. At temperatures well above 4 degrees, HDL dominates the liquid. HDL has collapsed structure with high packing efficiency, giving it high density around 1.1 grams per cubic centimeter. As water cools, thermal contraction brings molecules closer together, increasing density in the normal manner. However, cooling also shifts the LDL-HDL equilibrium toward LDL because LDL has lower enthalpy due to stronger hydrogen bonding. At high temperatures, entropy favors HDL despite its higher enthalpy. As temperature decreases, the entropic advantage diminishes and LDL populations grow. LDL has much lower density than HDL, approximately 0.94 grams per cubic centimeter, due to its open tetrahedral structure. As the LDL fraction increases with cooling, the overall density reflects the weighted average of LDL and HDL densities. At temperatures above 4 degrees, thermal contraction of both structural types dominates, and total density increases despite growing LDL populations. At 4 degrees, the two effects exactly balance. The rate of LDL growth with cooling produces volume expansion that precisely matches the thermal contraction, creating zero net density change. Below 4 degrees, LDL growth accelerates, and the structural expansion overwhelms thermal contraction, causing overall density to decrease. Quantitatively, the density as a function of temperature can be modeled as ρ equals x times ρ LDL plus 1 minus x times ρ HDL, where represents the molar fraction of LDL. If increases rapidly enough with decreasing temperature below 4 degrees, this equation naturally produces a density maximum. Computer simulations confirm this picture. By calculating the local tetrahedral order parameter for each molecule and classifying molecules as LDL-like or HDL-like based on threshold values, Researchers can track how populations evolve with temperature. The results show that LDL fractions near 0% at 100 degrees Celsius grow to approximately 25% at 4 degrees and continue increasing toward 50% near 0 degrees. The exact crossover composition, where density peaks, depends on the precise densities of pure LDL and HDL and how they vary with temperature. Different water models predict slightly different crossover points because they assign different relative stabilities to LDL and HDL. The TIP4P/2005 model places the density maximum at approximately 307 Kelvin, matching the experimental value of approximately 377 Kelvin closely. The agreement validates the model's accuracy in capturing the LDL-HDL balance. Compressibility measures how much volume decreases when pressure is applied, defined as -1 over volume times the derivative of volume with respect to pressure at constant temperature. For most liquids, compressibility decreases with increasing temperature because thermal expansion loosens molecular packing, making the structure more easily compressed. Water violates this expectation below approximately 319 Kelvin or 46 degrees Celsius. At lower temperatures, compressibility increases as temperature decreases, reaching a minimum at 46 degrees. This anomaly arises from the different compressibilities of LDL and HDL. LDL, with its open tetrahedral cages, is highly compressible. Applying pressure collapses the cage structures, forcing molecules into more compact arrangements without requiring large energy input. The voids inherent to tetrahedral networks provide space for molecules to move into under compression. HDL, already densely packed with molecules filling interstitial sites, resists further compression. Additional pressure must force molecules into unfavorable close contacts with high energetic cost. Consequently, pure LDL has compressibility roughly 3 times higher than pure HDL. Water's overall compressibility reflects the weighted average of LDL and HDL compressibilities, plus contributions from pressure-induced conversion between structural types. At temperatures above 46 degrees, where HDL dominates, increasing temperature further reduces the already small LDL fraction, decreasing overall compressibility. Below 46 degrees, cooling increases LDL fraction significantly, and since LDL is more compressible, overall compressibility increases. The minimum at 46 degrees marks the temperature where these competing effects balance, similar to the density maximum mechanism but involving different properties. Structural conversion contribution deserves emphasis. When pressure is applied to water containing both LDL and HDL, some LDL molecules convert to HDL because pressure favors the denser form. This conversion itself causes volume decrease beyond the simple compression of each structural type. Near the compressibility minimum, where both populations are substantial, pressure-induced conversion is most effective, contributing significantly to overall compressibility. This explains why the compressibility minimum appears at higher temperature than the density maximum. The pressure conversion effect peaks when populations balance, which occurs at higher temperature than where LDL begins dominating volume effects. Heat capacity measures the energy required to raise temperature by 1 degree, defined as the derivative of enthalpy with respect to temperature at constant pressure. Normal liquids show slowly decreasing heat capacity as temperature rises because vibrational modes become saturated. Water behaves normally above approximately 350 Kelvin, showing gradual heat capacity decrease. Below 350 Kelvin, heat capacity begins increasing as temperature decreases, rising dramatically in the supercooled regime. Measurements on confined supercooled water show heat capacity reaching approximately 218 joules per mole per Kelvin at 229 Kelvin. More than double the room temperature value of approximately 75 joules per mole per Kelvin. This anomalous increase arises from energy required for structural conversion between LDL and HDL. When water is heated at constant pressure, energy goes into increasing molecular kinetic energy, but also into converting LDL to HDL because higher temperatures favor HDL entropically. The enthalpy difference between LDL and HDL is approximately 7 kilojoules per mole based on simulation estimates. Converting substantial fractions of the population between structural types requires this energy in addition to normal thermal excitation. Near temperatures where LDL and HDL populations balance and conversion rates are highest, the heat capacity becomes very large because a small temperature change converts many molecules. This produces a maximum in heat capacity as a function of temperature. Supercooled water studies locate this maximum near 229 Kelvin at atmospheric pressure, precisely where other evidence suggests the liquid-liquid transition becomes accessible. Above the transition temperature, where water exists as a single phase, heat capacity remains elevated but finite. At the critical point itself, heat capacity would diverge to infinity due to critical fluctuations, but crystallization prevents reaching the critical point in bulk samples. Thermal expansion coefficient measures volume change with temperature, defined as 1 over volume times the derivative of volume with respect to temperature at constant pressure. This coefficient is positive for nearly all substances, meaning they expand when heated. Water shows negative thermal expansion below 4 degrees Celsius, meaning it contracts when heated in this range. This directly reflects the density maximum. At temperatures below 4 degrees, heating decreases LDL populations faster than thermal expansion increases volume, causing net contraction. Above 4 degrees, thermal expansion dominates and the coefficient becomes positive. The magnitude of the thermal expansion coefficient also behaves anomalously, showing a minimum near 46 degrees that mirrors the compressibility minimum. The two properties are thermodynamically related through Maxwell relations, so their similar anomalous behaviors are expected. Both reflect the balance between structural populations and how sensitively those populations respond to temperature and pressure changes. Near the conditions where populations balance, small perturbations in temperature or pressure cause large structural responses, producing large values of thermodynamic derivatives. Viscosity measures resistance to flow, quantifying how much force is required to make a liquid flow at a given rate. Most liquids show decreasing viscosity with increasing temperature because thermal energy helps molecules overcome energy barriers to motion. Water follows this pattern, with viscosity dropping from approximately 1.8 millipascal seconds at 0 degrees to approximately 0.28 millipascal seconds at 100 degrees Celsius. However, water shows an additional anomaly. Viscosity decreases when pressure is applied at temperatures below 33 degrees Celsius. This contradicts normal behavior where pressure increases viscosity by forcing molecules closer together and increasing friction. The viscosity anomaly under pressure arises because pressure converts LDL to HDL, and HDL has lower viscosity than LDL. LDL's rigid tetrahedral networks resist flow because molecules must break multiple strong hydrogen bonds simultaneously to rearrange. HDL's flexible, distorted bonding allows easier molecular motion. When pressure is applied below 33 degrees, where LDL fractions are substantial, conversion to HDL decreases the average rigidity, lowering viscosity. Above 33 degrees, where HDL already dominates, pressure effects return to normal, slightly increasing viscosity through standard compression mechanisms. Diffusion coefficient describes how quickly molecules migrate through the liquid, closely related to viscosity. Water's self-diffusion decreases anomalously rapidly as temperature drops in the supercooled regime. Measurements and simulations show that diffusion coefficient drops by more than 2 orders of magnitude between 250 Kelvin and 220 Kelvin, a much steeper decline than expected from simple Arrhenius behavior. This rapid decrease is called the fragile to strong transition, marking a change from fragile liquid dynamics with super Arrhenius temperature dependence to strong liquid dynamics with Arrhenius dependence. The two-state model explains this transition as the system becoming dominated by LDL, which has intrinsically slower dynamics than HDL. At high temperatures where HDL dominates, molecular motion is relatively facile. As temperature decreases and LDL populations grow, the average mobility decreases because LDL molecules are constrained by strong tetrahedral hydrogen bonds. The crossover from HDL-dominated to LDL-dominated occurs around 220 Kelvin, producing the observed dynamic transition. This interpretation links the thermodynamic properties like heat capacity maximum to dynamic properties like diffusion coefficient minimum, showing that both arise from the same underlying structural transition. Dielectric constant measures how well a material screens electric fields, depending on how easily molecular dipoles reorient in response to applied fields. Water has an unusually high dielectric constant of approximately 80 at room temperature, decreasing to approximately 55 at 100 degrees Celsius. This high value makes water an excellent solvent for ionic compounds. The temperature dependence shows anomalies similar to other properties. In the supercooled regime, dielectric relaxation times increase dramatically, indicating that molecular reorientations slow down faster than expected. The two-state model predicts different dielectric responses for LDL and HDL. LDL, with its open structure, allows greater orientational freedom for molecules to rotate their dipoles, producing higher polarizability and dielectric constant. HDL, with densely packed molecules, restricts rotational motion, yielding lower dielectric constant. The overall dielectric response reflects the weighted average of structural populations plus contributions from conversion between types. At low temperatures where LDL dominates, dielectric constant is high, but relaxation is slow due to strong hydrogen bonding that hinders rotation. Surface tension provides another property where water behaves unusually. Water has very high surface tension compared to most organic liquids, approximately 72 millinewtons per meter at room temperature. This high value reflects the strong hydrogen bonding that makes creating new surface area energetically costly. Surface tension decreases with increasing temperature as expected, but the rate of decrease shows anomalies. The temperature derivative of surface tension changes slope near the same temperatures where other anomalies appear, suggesting that LDL-HDL populations also influence surface properties. At surfaces, water molecules have fewer neighbors than in the bulk, potentially altering the LDL-HDL balance. Some studies suggest that surfaces stabilize LDL structures because the reduced coordination at surfaces makes tetrahedral arrangements less geometrically frustrated. If true, water surfaces might have different structural populations than the bulk, contributing to surface tension anomalies. However, probing surface structure remains challenging, and the connection between bulk two-state behavior and surface properties is still being explored. Speed of sound in water shows a maximum at approximately 74 degrees Celsius, another property where temperature dependence deviates from normal liquid behavior. Sound speed depends on both density and compressibility through the relation that speed equals the square root of the inverse of density times compressibility. The anomalous behaviors of both density and compressibility conspire to create the sound speed maximum. Below 74 degrees, increasing temperature increases sound speed despite decreasing density because compressibility decreases faster. Above 74 degrees, compressibility changes more slowly, and decreasing density causes sound speed to decrease. Virtually every anomalous property of water can be understood through the LDL-HDL competition. Properties that depend on structure, like density and compressibility, reflect the weighted averages of structural populations with different inherent values. Properties that depend on energy, like heat capacity and thermal expansion, reflect the energy required to convert between structural types. Properties that depend on dynamics, like viscosity and diffusion, reflect the different molecular mobilities in each structural environment. Properties that depend on dielectric response reflect the different polarizabilities and rotational freedoms of each structure. The two-state model transforms water from a collection of disconnected mysteries into a unified system with a single underlying cause for all its peculiarities. The model makes quantitative predictions that can be tested through simulation and experiment. As computational models improve and experimental techniques access deeper supercooled conditions, increasingly precise tests become possible. The agreement between predicted and observed anomalies validates the two-state picture and confirms that water's bizarre behaviors arise from its internal structural conflict between tetrahedral order and entropic disorder. This conflict is not abstract theory, but physical reality, frozen in ice polymorphs that reveal the diversity of structures water molecules can adopt. Chapter 11: Ice Polymorphism, the Frozen Battlefield. Ice is not a single substance, but a family of at least 20 distinct crystalline forms, each with different molecular arrangements and stability ranges. These polymorphs span pressures from negative values, where the most open structures exist, to hundreds of gigapascals, where molecules pack with extreme density. The diversity of ice structures reveals the geometric possibilities available to water molecules and provides crucial insight into liquid water's behavior. Polymorphs often come in pairs, with a hydrogen-disordered form transforming into a hydrogen-ordered form at low temperatures. This order-disorder transition reflects the same tensions between entropy and enthalpy that drive the liquid-liquid transition, making ice polymorphism the solid-state manifestation of water's split personality. Ice-I, pronounced Ice-1H, is the ordinary ice familiar from everyday experience. The H denotes hexagonal symmetry, distinguishing it from the rare Ice-Ike with cubic symmetry. In Ice-I, oxygen atoms form hexagonal rings stacked in layers with ABAB pattern. Each oxygen coordinates with 4 neighbors in perfect tetrahedral arrangement, forming hydrogen bonds at 109.5-degree angles. The nearest neighbor, oxygen-oxygen distance, measures 2.75 angstroms, identical to LDL. This structural similarity is no coincidence. Ice-I represents the crystalline version of LDL, with the same local coordination but extended to infinite periodicity. The hydrogen atoms in Ice-I are disordered, meaning they occupy random positions along the oxygen-oxygen bonds rather than adopting a unique periodic pattern. Each oxygen has 2 hydrogen atoms covalently bonded close to it at approximately 1 angstrom distance, and 2 hydrogen atoms from neighboring molecules bonded at approximately 1.75 angstroms distance. These positions satisfy the ice rules. Each oxygen has 2 close hydrogens and 2 distant hydrogens, and each oxygen-oxygen bond has exactly 1 hydrogen atom along it. However, which bonds have hydrogens close to which oxygen varies randomly throughout the crystal. This hydrogen disorder creates residual entropy even at absolute zero, violating the third law of thermodynamics, which states that entropy should vanish as temperature approaches zero. Linus Pauling calculated in 1935 that Ice-I has residual entropy of approximately 3.4 joules per mole per Kelvin, arising from the many ways to arrange hydrogen positions while satisfying ice rules. This entropy was later confirmed experimentally through calorimetry measurements. The existence of residual entropy indicates that Ice-I is not a true equilibrium crystal at low temperatures, but rather a frozen metastable state, unable to find its lowest energy configuration. Ice-I represents the hydrogen-ordered form of Ice-I. At temperatures below approximately 72 Kelvin, Ice-I should transform to Ice-I to eliminate residual entropy. However, the transformation is kinetically hindered and occurs only over geological timescales without catalysts. In 1972, researchers discovered that doping ice with small amounts of potassium hydroxide dramatically accelerates ordering. The hydroxide ions create defects that allow hydrogen atoms to hop between sites more easily, facilitating the search for ordered configurations. Ice-I samples produced by slow cooling of KOH-doped ice show orthorhombic symmetry with fully ordered hydrogen positions. The transformation from Ice-I to Ice-Xi is antiferroelectric, meaning neighboring dipoles point in opposite directions, producing zero net dipole moment. Ice Xi is slightly denser than Ice I because ordering allows tighter packing. The volume change is small, approximately 0.1%, but measurable. The ordering transition releases latent heat of approximately 1.3 kilojoules per mole, consistent with the residual entropy being removed. Ice Xi represents the true equilibrium low-temperature form of ordinary ice, though most naturally occurring ice remains as metastable Ice I. Ice Ike forms when water vapor deposits onto cold surfaces below approximately 150 Kelvin. It has cubic symmetry with oxygen atoms forming diamond-like structure where every carbon position in diamond is replaced by oxygen. The local tetrahedral coordination matches Ice I, but the stacking sequence differs. Ice Ike uses ABC stacking instead of AB stacking, creating cubic symmetry. Ice Ike is metastable relative to Ice I at all pressures, transforming irreversibly to Ice I when warmed above approximately 200 Kelvin. The energy difference between forms is small, only approximately 60 joules per mole, explaining why Ice Ike sometimes forms kinetically before converting to the more stable hexagonal form. Pressure creates polymorphs with different structures. Ice II forms when Ice I is compressed to approximately 300 megapascals at temperatures below 200 Kelvin. The structure becomes trigonal rather than hexagonal, with oxygen positions arranged into 4-membered and 8-membered rings. The hydrogen bonding network maintains tetrahedral coordination locally, but adopts different long-range topology. Ice II is denser than Ice I, with approximately 1.2 grams per cubic centimeter, but still less dense than liquid water because tetrahedral networks inherently waste volume. Ice II transforms to Ice I when decompressed, but the transition is slow at low temperatures where molecular mobility is limited. Ice III forms in a narrow pressure range around 300 megapascals between 0 and 250 Kelvin. Its structure is tetragonal with complex hydrogen bonding patterns, creating large channels through the crystal. Ice III is less dense than Ice II despite forming at similar pressure because its channels occupy significant volume. Warming Ice III at high pressure transforms it to Ice V, another tetragonal polymorph, but with different connectivity. These transformations highlight the sensitivity of ice structures to small changes in temperature and pressure, reflecting the many competing arrangements available to hydrogen bonding networks. Ice VI dominates at pressures between 1 and 2 gigapascals over a wide temperature range, extending to room temperature. Ice VI has unique structure containing 2 interpenetrating hydrogen bonding networks that do not directly connect to each other. Each network forms tetrahedral coordination, but the 2 networks occupy the same space, threading through each other like interlinked chain mail. The oxygen positions form body-centered tetragonal lattice. Ice VI is hydrogen disordered with residual entropy, allowing 2 different hydrogen-ordered forms. Ice XV represents the first hydrogen-ordered form of Ice VI, discovered in 2009 by doping Ice VI with hydrochloric acid and slowly cooling. The ordering is antiferroelectric with hydrogen positions arranged to minimize dipole moments. Ice XV has slightly larger volume than Ice VI, meaning it is favored at lower pressures. The transformation from Ice VI to Ice XV releases latent heat and shows first-order character with coexistence region. Ice XV can be recovered to atmospheric pressure and persists metastably up to approximately 130 Kelvin before disordering back to Ice VI. Ice XIX represents the second hydrogen-ordered form of Ice VI, discovered in 2021. Unlike Ice XV, Ice XIX is partially ordered rather than fully ordered, with some hydrogen positions remaining disordered even at low temperatures. Ice XIX forms at higher pressures than Ice XV, approximately 1.8 gigapascals, because its smaller unit cell volume makes it favored where pressure is higher. Ice XIX shows weak ferroelectric character, meaning it has a small net dipole moment, unlike the antiferroelectric Ice XV. The existence of 2 distinct ordered forms from the same disordered parent demonstrates that ice structures contain multiple competing arrangements with similar energies. Ice VII forms above approximately 2 gigapascals and persists to at least 60 gigapascals. It has body-centered cubic structure with oxygen atoms occupying simple cubic lattice sites. Like ice VI contains two interpenetrating hydrogen bonding networks. However, in ice VII, the symmetry is higher, making the two networks crystallographically equivalent. Ice VII is hydrogen disordered at high temperatures, but transforms to hydrogen-ordered ice VII upon cooling below approximately 260 Kelvin at most pressures. The ice VII to ice VII transformation is antiferroelectric and releases substantial latent heat. Ice VII differs from ice VII only in hydrogen ordering, with oxygen positions essentially identical. The ordered hydrogen arrangement in ice VII eliminates residual entropy, making it the true equilibrium low-temperature form in its pressure range. Ice VII has slightly higher density than ice VII because ordering allows molecules to pack more efficiently. The transformation between forms provides an example of order-disorder transition in high-pressure ice, analogous to the ice I to ice Xi transition at ambient pressure. Ice X forms above approximately 60 to 100 gigapascals, representing a fundamentally different state where the distinction between covalent and hydrogen bonds disappears. At extreme pressures, hydrogen atoms move to midpoints between oxygen atoms, forming symmetric hydrogen bonds. The oxygen-hydrogen distance increases from approximately 1 angstrom in normal ice to approximately 1.2 angstroms in ice X, while the hydrogen bond length decreases correspondingly. Ice X has body-centered cubic structure with oxygens on lattice sites and hydrogens centered on the bonds connecting them. This symmetric configuration makes ice X hydrogen-ordered by necessity since all bonds are equivalent. Ice X represents the predicted endpoint of hydrogen bond compression. At even higher pressures, above 200 gigapascals, ice X may transform to other structures with closer oxygen packing, but the hydrogen bonding concept becomes less meaningful as covalent and intermolecular interactions merge. Planetary scientists are particularly interested in ice X and higher pressure forms because they likely exist in the interiors of large icy moons and ice giant planets like Uranus and Neptune, where pressures reach hundreds of gigapascals. Ice XVII forms at negative pressures, meaning it is stabilized by mechanical tension rather than compression. This counterintuitive structure was discovered computationally and later confirmed experimentally by synthesizing it in hydrophobic nanopores, where confinement creates effective negative pressure. Ice XVII has extremely low density, approximately 0.81 grams per cubic centimeter, even lower than ice I. The structure contains large channels, making it open and porous. Ice XVII demonstrates that water can adopt structures even more open than familiar ice when conditions permit. Ice XVII is a superionic phase where oxygen atoms form a crystalline lattice, while hydrogen atoms diffuse freely through the structure like a fluid. This exotic state forms above 10 gigapascals and 1,500 Kelvin, requiring simultaneous high pressure and high temperature. In superionic ice, hydrogen atoms are no longer bound to specific oxygen atoms, but hop rapidly between sites, conducting electricity like ions in a solution. Experiments using laser-driven shock compression and diamond anvil cells with laser heating confirmed the existence of superionic ice in 2019. This phase likely exists in deep interiors of Uranus and Neptune, potentially explaining their anomalous magnetic fields. The discovery pace of ice polymorphs has accelerated in recent decades. Ice XIV was discovered in 2006, Ice XV in 2009, Ice XVI in 2014, Ice XVII in 2016, Ice XVII in 2019, and Ice XIX in 2021. Each discovery required developing new techniques or exploring previously inaccessible regions of temperature-pressure space. Computational predictions suggest additional polymorphs await discovery at ultra-high pressures or in metastable regions. The number 20 represents current confirmed polymorphs, but theoretical studies predict dozens more structures that might exist under special conditions. Transitions between ice polymorphs provide insight into the energy landscape of water structures. Many transitions show hysteresis, meaning different transformation pressures when compressing versus decompressing. This indicates substantial energy barriers between polymorphs despite small free energy differences. The barriers reflect the need to reorganize hydrogen bonding networks, breaking existing bonds and forming new patterns. At low temperatures where molecular motion is slow, these barriers can prevent equilibration for years or centuries. At higher temperatures, thermally activated processes facilitate transitions and equilibrium is reached quickly. The connection between ice polymorphism and liquid water structure is profound. Each ice polymorph represents a possible local structure that might exist in the liquid. Ice I corresponds to LDL with its tetrahedral networks. High-pressure ices like ice VII with distorted hydrogen bonding and interpenetrating networks correspond to HDL. The liquid can be viewed as containing fluctuating regions with various ice-like structures that constantly interconvert as thermal energy breaks and reforms bonds. The competition between different ice structures in the solid state mirrors the competition between different liquid structures in the liquid state. The multiplicity of hydrogen-ordered forms from single disordered parents, like ice XV and ice XIX, both deriving from ice VI, demonstrates that water molecules can adopt multiple ordered arrangements with similar energies. This multiplicity in solids suggests that liquids also contain multiple structural states in dynamic equilibrium. The order-disorder transitions in ices, driven by temperature and pressure, parallel the LDL-HDL transition in liquids. In both cases, low temperatures favor ordered, low-entropy structures with strong bonding, while high temperatures favor disordered, high-entropy structures. Pressure favors dense structures regardless of order. Ice polymorphism reveals that hydrogen bonding, despite being relatively simple conceptually, creates extraordinarily complex energy landscapes with many competing structures. Small changes in conditions tip the balance between structures, producing rich phase diagrams. Understanding this complexity in ordered crystalline phases provides foundation for understanding liquid water, where the same structural diversity exists, but averaged over time and space rather than locked into periodic patterns. The frozen battlefield of ice polymorphs charts the territory where the liquid-state war between structural tendencies is fought. Chapter 12: Molecular Dynamics Simulations. Computer simulations have become indispensable for understanding water at the molecular level. Experimental techniques can measure macroscopic properties and sometimes probe structure through scattering, but they cannot directly observe individual molecules moving and interacting. Simulations bridge this gap by numerically solving the equations governing molecular motion, generating detailed trajectories showing exactly where each molecule is located and how it moves over time. These simulations require accurate mathematical models of the forces between molecules, computational resources to track thousands or millions of molecules, and sophisticated analysis methods to extract meaningful information from enormous datasets. Molecular dynamics, abbreviated MD, represents the most widely used simulation technique for liquids. In MD simulations, each molecule is treated as a point mass or rigid body with specific position and velocity. The forces acting on each molecule arise from interactions with neighboring molecules, calculated using a potential energy function called a force field or water model. Newton's second law, force equals mass times acceleration, determines how velocities change in response to forces. Integrating the equations of motion forward in tiny time steps, typically 1 femtosecond or 1/millionth of 1/billionth of a second, generates trajectories showing molecular positions and velocities as functions of time. The accuracy of MD simulations depends critically on the water model employed. Early models like TIP-3P, developed in 1983, represented water molecules as rigid triangles with point charges at the 3 atomic positions. These 3-site models captured the basic electrostatic and geometric features of water, but lacked the sophistication needed to reproduce detailed properties accurately. They predicted qualitatively correct behavior like tetrahedral coordination and hydrogen bonding, but quantitative agreement with experiment was poor. Density, heat of vaporization, diffusion coefficients, and other properties deviated from experimental values by 10 to 30%. Improvements came from adding more interaction sites. The TIP4P model, introduced in 2000, places a fourth interaction site representing the oxygen lone pairs offset from the atomic positions. This modification better captures the electrostatic potential around the molecule, improving agreement with quantum mechanical calculations. TIP4P/2005 represents an optimized version of this model, with parameters adjusted to reproduce multiple experimental properties simultaneously. This model achieves remarkable accuracy, predicting density within 1%, heat of vaporization within 2%, and self-diffusion coefficients within 10% over wide temperature ranges. The TIP4P/2005 model reproduces water's anomalous properties, including the density maximum near 4 degrees Celsius and the compressibility minimum near 46 degrees Celsius. More dramatically, it predicts a liquid-liquid phase transition in the supercooled regime, with a critical point located near 193 Kelvin and 50 megapascals, according to detailed free energy calculations. The model shows spontaneous phase separation into LDL and HDL domains when equilibrated at appropriate conditions, confirming that the model's energy landscape contains two distinct structural basins. This success validates the model as capturing the essential physics of water interactions. Other popular models include SBC/E, a 3-site model with slightly different parameters optimized for extended simulations, and TIP5P, a 5-site model with 2 sites representing lone pairs. Each model represents different compromises between accuracy and computational efficiency. 5-site models generally achieve better accuracy, but require more computation per time step, because more interaction sites mean more pairwise force calculations. 3-site models are fastest, but least accurate. 4-site models occupy a middle ground, offering good accuracy at reasonable computational cost. The monatomic water model, abbreviated MW, takes a radically different approach. Instead of explicitly representing hydrogen atoms, MW treats each water molecule as a single interaction site with angle-dependent forces that mimic tetrahedral coordination. This coarse graining dramatically reduces computational cost because the number of sites per molecule decreases by 3-fold. Despite the simplification, MW reproduces many water properties surprisingly well, including the liquid-liquid transition and multiple ice polymorphs. The success of MW suggests that tetrahedral geometry is more important than detailed electrostatic interactions for determining structural properties, though the model fails for phenomena requiring explicit hydrogen dynamics. Many-body polarizable models represent the next level of sophistication. Simple models like TIP4P treat each molecule's charge distribution as fixed, ignoring how neighboring molecules polarize each other. In reality, the dipole moment of a water molecule increases from 1.85 dBi in the gas phase to approximately 2.6 dBi in the liquid due to mutual polarization. Many-body models account for this by making dipole moments self-consistently adjustable. The MBPOL model, developed starting in 2012, incorporates explicit many-body terms up to 4-body interactions, calibrated against high-level quantum chemistry calculations. MBPOL achieves near-quantum accuracy for many properties, reproducing not just bulk water behavior, but also small cluster structures, vibrational spectra, and properties across the entire phase diagram. The model correctly predicts the melting points of multiple ice polymorphs and the liquid-liquid transition location. Simulations using MBPOL provide the most reliable predictions available from classical molecular dynamics. However, MBPOL requires substantially more computation than simpler models, limiting simulation sizes to thousands of molecules and timescales to nanoseconds rather than the millions of molecules and microseconds accessible with simpler models. Ab initio molecular dynamics, abbreviated AIMD, avoids empirical force fields entirely by calculating forces from quantum mechanics on the fly during the simulation. At each time step, the electronic structure is computed using density functional theory or similar methods. Then forces on nuclei are derived from the energy gradients. AIMD provides the ultimate accuracy for molecular simulations, but is computationally expensive, limiting systems to hundreds of molecules and timescales to picoseconds. AIMD has been crucial for studying water because it captures effects like charge transfer and polarization that empirical models approximate or ignore. AIMD simulations confirm the existence of structural heterogeneity in liquid water, showing bimodal distributions of local order parameters consistent with LDL and HDL populations. AIMD also helped resolve controversies about X-ray absorption spectra by providing predictions of how different hydrogen bonding environments affect electronic structure. While AIMD cannot access the long timescales and large systems needed to observe liquid-liquid phase separation directly, it validates simpler models by showing that their structural predictions agree with quantum mechanics. Running MD simulations involves several technical considerations. The system must be placed in a simulation box with periodic boundary conditions to eliminate surface effects and approximate bulk behavior. Temperature and pressure must be controlled using thermostats and barostats that add or remove energy and adjust box volume to maintain target conditions. Integration algorithms must be chosen carefully to conserve energy and avoid numerical instabilities. Equilibration periods are required to allow systems to relax from artificial initial configurations before production data collection begins. Analyzing MD trajectories requires calculating various properties and correlations. Radial distribution functions are computed by histogramming distances between molecules as functions of separation. Order parameters like tetrahedral order or orientational order are calculated for each molecule based on neighbor positions and orientations. Thermodynamic properties like pressure and energy are averaged over trajectories. Dynamic properties like diffusion coefficients are extracted from mean-squared displacements or velocity autocorrelation functions. Hydrogen bond networks are identified by applying geometric criteria to define when bonds exist. Studying the liquid-liquid transition through MD requires enhanced sampling techniques because spontaneous phase separation is rare in normally equilibrated systems. Umbrella sampling, metadynamics, and transition path sampling are methods that bias simulations to explore rare regions of configuration space, allowing calculation of free energy landscapes and transition rates. These techniques revealed that LDL and HDL represent distinct free energy minima separated by barriers of several kilojoules per mole. The barrier height determines how frequently molecules interconvert between states. Path integral molecular dynamics, abbreviated PIMD, incorporates quantum effects on nuclear motion that classical MD neglects. At low temperatures, hydrogen atoms are light enough that quantum delocalization becomes important. PIMD treats each nucleus as a ring polymer of fictitious beads whose distribution represents the quantum position uncertainty. PIMD simulations of water show that quantum effects increase disorder and decrease structural correlations compared to classical simulations. The liquid-liquid critical point shifts to lower temperature by approximately 10 Kelvin when quantum effects are included, bringing theoretical predictions closer to experimental estimates. Machine learning has recently revolutionized molecular simulation by enabling development of potentials combining accuracy near quantum methods with computational efficiency near empirical models. Neural network potentials trained on large databases of quantum chemistry calculations can interpolate energies and forces for arbitrary configurations with near quantum accuracy. These potentials enable microsecond MD simulations with accuracy previously achievable only on picosecond timescales. Machine-learned potentials for water are actively being developed and promise to enable unprecedented studies of rare events like homogeneous ice nucleation and liquid-liquid phase separation. Simulations have limitations despite their power. Force fields contain approximations that introduce systematic errors. Finite system sizes can distort properties, especially near phase transitions where correlation lengths diverge. Limited timescales may miss slow processes like crystallization or large-scale structural relaxation. Interpreting simulation results requires understanding these limitations and validating predictions against experiments whenever possible. The interplay between simulation and experiment, with each informing and correcting the other, has proven essential for advancing water science. The development of accurate water models required decades of effort by many research groups. Each generation of models improved upon predecessors by incorporating more physics or better parameter optimization. The current state of the art, represented by models like TIP4P/2005, MBPOL, and neural network potentials, achieves unprecedented accuracy and reliability. These models not only reproduce known experimental properties, but also make testable predictions about phenomena in experimentally inaccessible regions. The validation of liquid-liquid transition predictions through ultra-fast experiments represents a triumph for computational water science. Looking forward, simulations will continue pushing toward larger systems, longer times, and higher accuracy. Exascale supercomputers coming online enable billion-atom simulations that can model macroscopic phase separation and heterogeneous nucleation. Improved quantum methods combined with machine learning will provide force fields approaching exact quantum accuracy. These advances will enable answering long-standing questions about how water behaves in extreme conditions, how ice nucleation occurs, and how water's unique properties enable biological function. Molecular dynamics has matured from a niche technique to an essential tool for understanding water at the molecular level, revealing the hidden structures and dynamics underlying macroscopic behavior. Chapter 13: The Two-State Model Framework. The two-state model provides a rigorous thermodynamic framework for understanding water's behavior by treating the liquid as a mixture of two distinct structural populations in dynamic equilibrium. This theoretical foundation translates qualitative observations about structural diversity into quantitative predictions that can be tested against experiments and simulations. The model requires defining order parameters that distinguish structural states, constructing free energy landscapes that describe their relative stability, and calculating how macroscopic properties emerge from the weighted contributions of each population. Understanding this framework reveals why water behaves so differently from simple liquids and how molecular structure determines bulk thermodynamics. Order parameters serve as coordinates that quantify structural characteristics. For water, the most important order parameter measures tetrahedral coordination quality. The tetrahedral order parameter, commonly denoted Q, evaluates the arrangement of the four nearest neighbors around each molecule. Perfect tetrahedral geometry yields Q equals 1, while random arrangements give Q near 0. The mathematical definition involves calculating angles between vectors pointing from the central molecule to its neighbors, then comparing these angles to the ideal tetrahedral angle of 109.5 degrees. Specifically, Q equals 1 minus 3 over 8 times the sum over j less than k of the quantity cosine of psi jk plus 1/3 squared, where psi jk represents the angle formed by the central molecule and neighbors j and k for perfect tetrahedral coordination. All angles equal 109.5 degrees, making cosine of psi equal negative 1/3, so each term in the sum vanishes and Q equals 1. For collapsed or distorted coordination, angles deviate from ideal values, producing positive contributions to the sum and reducing Q below 1. Random arrangements give Q approximately 0.1 to 0.3. Computing Q for every molecule in a simulation or experimental configuration generates a distribution showing how many molecules have each Q value. For simple liquids without directional bonding, this distribution is narrow and centered near low Q values. For water, the distribution is broader and often shows bimodal character with peaks near Q equals 0.7 corresponding to LDL and Q equals 0.3 corresponding to HDL. The separation between peaks grows more distinct at low temperatures where structural populations separate more clearly. The Q distribution provides direct visual evidence for the two-state nature of water. Another useful order parameter measures translational order rather than angular order. The local structure index, abbreviated LSI, quantifies the separation between the first and second coordination shells. LSI examines the distance from a central molecule to its neighbors, identifying how clearly the first shell of approximately 4 closest neighbors separates from more distant second shell neighbors. Well-defined shells produce high LSI values, while interpenetrating shells where second neighbors intrude into first shell distances produce low LSI. LDL shows high LSI because tetrahedral structures maintain clear shell separation. HDL shows low LSI because collapsed structures allow interstitial occupation that blurs shell boundaries. The relationship between different order parameters reveals correlations between structural features. Molecules with high tetrahedral order Q typically also show high translational order LSI, indicating that these characteristics go together in LDL environments. Molecules with low Q typically show low LSI, both signatures of HDL. Plotting Q versus LSI for all molecules creates order maps where LDL and HDL populate distinct regions. These maps provide comprehensive structural characterization, more informative than single order parameters alone. Free energy landscapes describe the thermodynamic stability of different structural states. The landscape is constructed by calculating the probability of observing particular order parameter values, then converting probability to free energy through the relation free energy equals negative kBt times natural logarithm of probability, where kb is Boltzmann constant and T is temperature. Peaks in probability correspond to valleys in free energy, representing stable states. The free energy landscape for water, as a function of Q, shows two minima at low temperatures, one near Q equals 0.7 for LDL and one near Q equals 0.3 for HDL. The depth and separation of these minima change with temperature and pressure. At very low temperatures around 180 Kelvin at atmospheric pressure, the LDL minimum is much deeper than HDL, meaning LDL is thermodynamically favored and dominates the population. As temperature increases, the HDL minimum deepens while the LDL minimum becomes shallower, reflecting entropy favoring HDL. At approximately 220 Kelvin, the two minima have equal depth, indicating equal populations. Above this temperature, HDL becomes favored. The barrier between minima determines how easily molecules interconvert between states. Pressure affects the landscape differently than temperature. Increasing pressure raises the free energy of LDL relative to HDL because LDL occupies more volume. The effect is to shift the entire LDL minimum upward in the free energy landscape, making HDL increasingly favored. At sufficiently high pressure, the LDL minimum disappears entirely, leaving only HDL as a stable state. The critical point represents conditions where the barrier between minima vanishes, allowing continuous transformation rather than first-order phase separation. The two-state model makes quantitative predictions for thermodynamic properties. The density equals x times rho LDL plus 1 minus x times rho HDL, where is the molar fraction of LDL molecules. If rho LDL equals 0.94 grams per cubic centimeter and rho HDL equals 1.14 grams per cubic centimeter, and if varies with temperature according to equilibrium between states, the model reproduces the density maximum. The key is that X increases rapidly enough with cooling below 4 degrees Celsius that the structural contribution to density overwhelms thermal contraction. Heat capacity predictions require knowing the enthalpy difference between states. If HHDL minus HLDL equals 7 kilojoules per mole, then heating water requires energy both to increase molecular kinetic energy and to convert LDL to HDL. The total heat capacity equals the ideal gas contribution plus the structural contribution, which is delta H squared over RT squared times the derivative of X with respect to temperature. Near the transition temperature, where X changes rapidly, this structural contribution becomes large, creating the observed heat capacity maximum. Compressibility predictions follow similar logic. The volume equals X times V LDL plus 1 minus times V HDL, where V denotes molar volume. Pressure causes both direct compression of each structural type and conversion between types. The compressibility equals the weighted average of structural compressibilities plus a conversion term proportional to the pressure derivative of X times the volume difference. This naturally produces a compressibility minimum at conditions where population sensitivity to pressure peaks. The Weidem line provides a unifying concept connecting thermodynamic and dynamic anomalies. The Weidem line extends from the liquid-liquid critical point into the single-phase region above the critical temperature, following the locus of maximum correlation length. Crossing the Weidem line produces sharp but continuous changes in properties, distinguishing liquid-like from gas-like or LDL-like from HDL-like behavior. Water's anomalies are most pronounced along the Weidem line because this is where fluctuations between structural states are largest. Response functions like heat capacity, compressibility, and thermal expansion coefficient all show maxima along the Weidem line. These maxima reflect the large susceptibility of the system to external perturbations when structural populations are balanced and correlation lengths are long. Far from the Weidem line, either LDL or HDL dominates, structural responses are small, and properties follow normal liquid behavior. Near the Weidem line, structural responses are large, amplifying thermodynamic derivatives and creating anomalies. Dynamic properties also show crossovers at the Weidem line. The fragile to strong transition in diffusion and viscosity occurs where the liquid crosses from HDL-dominated to LDL-dominated regions. HDL has fragile dynamics with superhomogeneous temperature dependence because activated processes involve overcoming barriers that grow as temperature decreases. LDL has strong dynamics with homogeneous temperature dependence because the rigid hydrogen bond network creates barriers less sensitive to temperature. The crossover represents the structural transition averaged over fluctuating domains. The Weidem line in supercooled water has been mapped through simulations and experiments. For the TIP4P/2005 model, the line extends from the critical point near 193 Kelvin and 50 megapascals upward toward higher temperatures at pressures below 50 megapascals. At atmospheric pressure, the Weidem line crosses around 220 Kelvin, matching where heat capacity and other anomalies peak. Confined water experiments show dynamic crossovers consistent with Weidem line predictions, supporting the model's validity. Critical phenomena near the liquid-liquid critical point produce universal behaviors independent of microscopic details. As the critical point is approached, the correlation length diverges as a power law, correlation length proportional to T to the negative nu power, where T equals absolute value of temperature minus critical temperature divided by critical temperature measures distance from the critical point, and nu approximately equals 0.63 is a universal exponent. Similarly, heat capacity diverges as T to the negative alpha power, with alpha approximately equals 0.11. These universal exponents apply to all second-order phase transitions in the Ising universality class. Water's anomalies can be understood as precursors of critical divergences. Although the critical point lies in no man's land where crystallization prevents direct observation, its presence nearby creates large but finite correlation lengths and response functions in the accessible supercooled regime. The power law divergences are cut off by crystallization, producing maxima rather than infinities, but the underlying critical behavior shapes the temperature and pressure dependence. This connection between water's anomalies and critical phenomena represents a profound insight from the two-state framework. Mathematical formulations of the two-state model vary in sophistication. The simplest approach treats LDL and HDL as independent components with fixed properties, calculating mixture properties as weighted averages. More sophisticated models allow structural properties to vary continuously while maintaining bimodal population distributions. The most advanced approaches compute free energies from first principles using statistical mechanics, deriving equilibrium populations from energy landscapes without assuming functional forms. All approaches predict qualitatively similar behavior but differ in quantitative details. The Van der Waals-like formulation treats LDL and HDL as phases separated by a critical point, analogous to liquid-gas transitions. This approach uses an equation of state with parameters adjusted to reproduce water's properties. The model naturally produces coexistence curves, critical points, and metastable regions. Limitations arise from the mean field nature of Van der Waals equations, which neglect fluctuations important near critical points. Improved formulations incorporate fluctuation corrections to achieve better quantitative agreement. The lattice model approach places water molecules on a lattice where each site can be in LDL or HDL state. Interactions between neighboring sites favor or disfavor particular configurations, creating an effective Hamiltonian. Statistical mechanics then determines equilibrium populations and correlations. Lattice models capture the essential physics of structural competition while remaining computationally tractable for calculating phase diagrams and response functions. They provide intuitive pictures of how local interactions produce macroscopic behavior. The two-state model transforms water from an enigma into an understandable system. By recognizing that structure matters and that water contains distinct structural populations in dynamic equilibrium, the model explains decades of puzzling observations through a unified framework. The success of this framework in predicting experimental results and organizing disparate phenomena validates the underlying hypothesis that water's peculiarities arise from its internal conflict between tetrahedral and collapsed structures. This conflict is not an abstract concept, but a concrete reality measurable through order parameters, visible in free energy landscapes, and manifested in every anomalous property water exhibits. Chapter 14: Implications for Chemistry and Biology. Water's dual structural nature has profound implications beyond fundamental physics, affecting chemistry, biology, and countless technological processes. The competition between low-density and high-density liquid structures influences how water dissolves substances, how it interacts with biological molecules, and how it enables or inhibits chemical reactions. Understanding these implications requires recognizing that water is not a passive background medium, but an active participant whose structure adapts to and influences its surroundings. The two-liquid framework provides new perspectives on phenomena from protein folding to cell membrane function to the possibility of life in extreme environments. Solvation, the process by which water surrounds and stabilizes dissolved molecules, depends critically on water's local structure. When ions dissolve in water, they disrupt hydrogen bonding networks in their immediate vicinity, creating hydration shells with different structure than bulk water. Small, highly charged ions like sodium or fluoride strongly polarize surrounding water molecules, forcing them into ordered shells reminiscent of ice structures. These hydration shells resemble LDL more than HDL because the strong ion-water interactions organize tetrahedral coordination despite entropic costs. Larger ions with lower charge density, like potassium or chloride, produce weaker perturbations, allowing water to maintain structures closer to bulk average. The competition between ion-induced ordering and thermal disorder determines hydration shell properties, including size, lifetime, and dynamics. Recognizing that bulk water already contains structural heterogeneity helps explain why different ions produce different effects. Ions that stabilize LDL-like structures have different thermodynamic and dynamic effects than ions that favor HDL-like structures. This structure-making versus structure-breaking classification, proposed decades ago, gains mechanistic understanding through the two-state framework. Protein folding represents perhaps the most important biological phenomenon influenced by water structure. Proteins are chains of amino acids that must fold into specific three-dimensional shapes to function. The folding process is driven primarily by the hydrophobic effect, the tendency of nonpolar amino acids to cluster together away from water. Traditional explanations view this as water avoiding contact with hydrophobic surfaces to preserve hydrogen bonding. The two-state perspective adds nuance by recognizing that different water structures respond differently to hydrophobic solutes. LDL, with its rigid tetrahedral networks, pays a large entropic cost to accommodate hydrophobic surfaces because creating cavities disrupts multiple hydrogen bonds. HDL, with flexible distorted networks, accommodates hydrophobic solutes more easily because fewer strong bonds must be broken. Consequently, the hydrophobic effect is stronger in cold water where LDL dominates than in hot water where HDL dominates. This explains why protein stability often shows maxima near room temperature, decreasing both at higher temperatures where the hydrophobic effect weakens and at lower temperatures where other factors dominate. Recent simulations suggest that water near hydrophobic protein surfaces is enriched in HDL-like structures because these structures better accommodate the interfacial geometry without severe energetic penalties. The protein effectively stabilizes HDL populations in its vicinity, creating a depleted LDL shell. This structural perturbation extends several molecular diameters from the surface, creating a spatially varying two-state composition around proteins. The perturbed shell influences protein-protein interactions, aggregation, and recognition processes by altering the effective forces between proteins mediated by intervening water. Hydrophilic interactions involving polar amino acids that hydrogen bond with water show opposite behavior. Polar surfaces stabilize LDL-like structures because they provide hydrogen bonding partners that substitute for water-water bonds. Proteins contain complex patterns of hydrophobic and hydrophilic residues, creating heterogeneous local water environments. The intricate interplay between these environments and protein structure determines folding pathways, stability, and function. Mutations that change amino acid hydrophobicity can alter nearby water structure, propagating effects through the protein. Enzymatic catalysis depends on precise positioning of substrates and catalytic residues, often involving water molecules as participants. Active sites of enzymes contain carefully arranged water molecules that accept or donate hydrogen bonds at critical steps in reaction mechanisms. Understanding that these water molecules can adopt different structural states depending on local environment provides insight into how enzymes control reactivity. Stabilizing particular water structures can lower activation barriers for desired reactions while raising them for side reactions, contributing to enzyme specificity. Cell membranes consist of lipid bilayers separating aqueous compartments. The interface between water and lipid head groups creates unique structural environments. Lipid phosphate groups are strong hydrogen bond acceptors that organize interfacial water into relatively ordered layers. These interfacial layers resemble LDL more than bulk water, with lifetimes extended from picoseconds in bulk to tens of picoseconds at interfaces. The ordered interfacial water influences membrane properties, including permeability, elasticity, and interactions with membrane proteins. Membrane proteins rely on precise hydration for function. Ion channels, which allow selective passage of ions across membranes, contain hydrophobic pores lined with carbonyl groups that substitute for water-hydrogen bonds. The structure of water inside these nanoscale pores differs from bulk water, often showing single-file arrangements where molecules cannot pass each other. The LDL-HDL balance inside pores depends on pore diameter, polarity, and confinement effects. These factors determine conductance, selectivity, and gating properties of ion channels. Cryopreservation, the preservation of biological materials through freezing, faces challenges from ice crystal formation that damages cells. Vitrification, creating glassy amorphous ice instead of crystalline ice, avoids damage but requires extremely rapid cooling or high concentrations of cryoprotectant chemicals. Understanding water's glass transition and the LDL-HDL competition provides strategies for optimizing vitrification protocols. Cryoprotectants that stabilize HDL-like structures may lower the glass transition temperature, making vitrification more accessible. Recent advances in vitrification have enabled cryopreservation of organs and tissues previously considered impossible. Protocols involve loading tissues with cryoprotectant mixtures, cooling to temperatures below the glass transition around 130 to 160 Kelvin, storing indefinitely, then warming and removing cryoprotectants. Success depends on avoiding crystallization during both cooling and warming. The warming phase is particularly challenging because ice nucleation kinetics peak near 160 Kelvin. Rapid warming through this temperature range, combined with stabilizing HDL structures that resist crystallization, improves viability. Confined water in biological systems exhibits properties different from bulk water due to both confinement effects and interactions with confining surfaces. Water inside protein cavities, between membrane bilayers, or within nanoporous materials shows altered dynamics, structure, and phase behavior. Some confinement environments stabilize LDL preferentially, others favor HDL, depending on pore size and surface chemistry. These variations influence biological function, as confined water participates in everything from protein stability to molecular transport. Astrobiology, the study of life in extreme environments and beyond Earth, increasingly recognizes water's unique properties as central to habitability. Liquid water is considered essential for life as we know it, making subsurface oceans on icy moons like Europa and Enceladus prime targets for life detection. These oceans exist at high pressures under kilometers of ice, placing them in thermodynamic regimes where water's behavior differs from familiar surface conditions. Understanding how water's properties change under pressure informs models of ocean composition, circulation, and habitability. Europa's ocean, estimated at depths of 80 to 100 kilometers beneath the ice shell, experiences pressures of approximately 100 to 150 megapascals at the ocean floor. At these pressures and near freezing temperatures, water exists near the liquid-liquid transition region. Whether Europa's ocean contains significant LDL populations or is dominated by HDL depends on exact pressure-temperature conditions. If LDL populations are substantial, this could affect ocean density structure, convection patterns, and the distribution of dissolved gases and nutrients. Enceladus, smaller than Europa, has a thinner ice shell of approximately 20 to 40 kilometers over a global or regional ocean. Pressures are correspondingly lower, perhaps 20 to 50 megapascals at depth. Recent observations of geysers erupting from Enceladus' south pole reveal that the ocean contains salts, organic molecules, and possibly hydrothermal activity. The two-state properties of water at these conditions influence ocean chemistry, including pH, ionic speciation, and reaction equilibria relevant to prebiotic chemistry and metabolism. High-pressure ice phases that form at ocean floors of large icy worlds might include ice VI or VII, depending on depth. The interfaces between high-pressure ice and liquid water host potentially unique chemistry. Water structure at these interfaces likely differs from bulk liquid, possibly showing enhanced LDL character near ice surfaces. If life exists in these environments, it must adapt to extreme pressures, low temperatures, and unusual water properties. Enzymes and cell membranes would need to function where water behaves quite differently than in terrestrial oceans. The search for biosignatures in subsurface oceans faces challenges because organic molecules degrade under radiation and oxidation. Understanding how water structure affects organic molecule stability informs mission planning for sample collection and analysis. If LDL structures preserve organic molecules better than HDL structures due to reduced reactivity, this could guide where to search for the most promising samples. Conversely, if HDL environments accelerate prebiotic synthesis, they might represent sites where life originated. Water's dual nature also impacts Earth's climate system through its role in clouds, ice formation, and ocean circulation. Supercooled cloud droplets, which remain liquid below 0 degrees Celsius, show properties influenced by growing LDL populations. These structural changes affect droplet size distributions, nucleation rates, and interactions with aerosol particles that seed ice crystals. Climate models require accurate representations of cloud microphysics, making water's supercooled properties directly relevant to climate predictions. Ocean circulation depends on water density variations driven by temperature and salinity. The density maximum at 4 degrees Celsius profoundly influences freshwater lake stratification and overturning. In polar oceans, cold water formation drives thermohaline circulation that redistributes heat globally. Climate change is altering these circulation patterns by warming and freshening surface waters, increasing stratification that inhibits mixing. Understanding how LDL-HDL populations respond to changing conditions helps predict circulation changes and their impacts on climate and ecosystems. Water's influence on chemistry and biology extends far beyond these examples. From drug design requiring understanding of how water mediates protein-ligand binding, to industrial processes like crystallization, where water structure affects nucleation and growth, to atmospheric chemistry, where water participates in ozone depletion and pollutant transformation, the two-liquid framework provides insights applicable across disciplines. Recognizing water's complexity rather than treating it as a simple background medium opens new avenues for understanding and manipulating chemical and biological systems. The internal war between structural states manifests in every aqueous environment, influencing outcomes in ways we are only beginning to appreciate. Chapter 15: Technological Applications and Future Research. The practical applications of understanding water's two-liquid nature span multiple industries and technologies. Desalination, which converts seawater to freshwater, relies on membranes that separate water molecules from dissolved salts. These reverse osmosis membranes exploit water's unusual transport properties, which depend on how molecules in different structural states interact with membrane materials. LDL, with its strong hydrogen bonding network, diffuses more slowly than HDL through confined spaces. Membrane materials that preferentially transmit HDL-like structures could achieve higher water flux while maintaining salt rejection. Current reverse osmosis membranes are made from polyamide thin films with nanoscale pores that physically exclude hydrated ions while allowing water passage. The performance depends on membrane thickness, porosity, and surface chemistry. Water structure within nanopores differs from bulk water, influenced by confinement and interactions with pore walls. Some research suggests that hydrophobic pores favor HDL-like structures with faster transport, while hydrophilic pores stabilize LDL-like structures with slower transport. Optimizing pore properties could improve energy efficiency of desalination, crucial as freshwater scarcity intensifies globally. Advanced desalination technologies, including forward osmosis and membrane distillation, also depend on water structure at interfaces and in confined geometries. Forward osmosis uses concentrated draw solutions to extract water through membranes without applied pressure, reducing energy costs. The osmotic driving force depends on chemical potential differences influenced by water structure around solutes. Membrane distillation exploits vapor-liquid equilibrium differences across porous hydrophobic membranes, with water structure affecting both vapor pressure and condensation kinetics. Materials science benefits from understanding how water structure influences surface properties. Antifreeze proteins produced by polar fish inhibit ice crystal growth by binding to ice surfaces and disrupting growth kinetics. These proteins have specific binding sites that recognize ice crystal faces through complementary hydrogen bonding patterns. Designing synthetic antifreeze materials requires understanding what water structures exist at protein-ice interfaces and how proteins stabilize particular configurations. Success could enable better cryoprotectants, anti-icing coatings for aircraft and infrastructure, and improved frozen food preservation. Hydrogels, polymer networks swollen with water, exhibit properties determined by water-polymer interactions. The water inside hydrogels shows altered dynamics and structure compared to bulk water, depending on polymer chemistry and cross-link density. Hydrogels designed for biomedical applications, including tissue engineering, drug delivery, and wound dressings, require water that mimics biological environments. Understanding LDL-HDL populations in hydrogels helps predict mechanical properties, swelling behavior, and biocompatibility. Supercapacitors and batteries often use aqueous electrolytes, where water structure influences ionic transport and electrochemical reactions. Water molecules in electrolytes coordinate with ions and interact with electrode surfaces, creating electric double layers that store charge. The capacitance and power density depend on how water reorganizes at charged interfaces under applied voltage. Electrolytes containing LDL-rich structures might show different charging kinetics than HDL-rich electrolytes, providing opportunities for performance optimization. Hydrogen production through water splitting, a key technology for renewable energy storage, requires catalysts that facilitate breaking water's oxygen-hydrogen bonds. The catalytic process involves water molecules adsorbing onto catalyst surfaces, donating electrons, and releasing oxygen gas. The efficiency depends partly on water structure at catalyst-water interfaces. Catalysts that stabilize particular water structures during intermediate reaction steps could lower overpotentials and increase production rates. Computational screening, guided by understanding of water structure-reactivity relationships, accelerates catalyst discovery. Climate science requires accurate models of ice nucleation in clouds to predict precipitation, radiation balance, and storm intensity. Ice nucleation depends on water structure fluctuations that create ice-like clusters large enough to grow spontaneously. The nucleation rate is exquisitely sensitive to temperature, with orders of magnitude changes over few degrees. Current models use empirical parameterizations that struggle to capture observed behavior. Mechanistic models based on LDL as a precursor to ice nucleation show promise for improving predictions and understanding cloud physics. Concrete, the most widely used building material globally, contains water that participates in hydration reactions, forming calcium silicate hydrate gel. The structure of water within this gel influences mechanical properties, durability, and resistance to freezing damage. Concrete exposed to freeze-thaw cycles suffers from expansion when pore water freezes, creating cracks. Understanding how confined water in nanopores behaves during cooling, including possible glass transitions or partial freezing, informs strategies for more durable concrete formulations. Pharmaceutical manufacturing involves crystallization of active ingredients from aqueous solutions, where crystal polymorph, size, and purity depend on water-solute interactions during nucleation and growth. Water structure around solute molecules influences aggregation kinetics and critical cluster formation. Controlling solution conditions, including temperature, pressure, and additives to manipulate water structure, offers pathways to reproducible crystallization outcomes, critical for drug efficacy and regulatory approval. Despite tremendous progress, major questions remain unanswered. The exact location of the liquid-liquid critical point in real water continues to be debated, with estimates spanning 20 Kelvin in temperature and 100 megapascals in pressure. Pinpointing this location requires experiments that access no man's land for extended times, challenging but potentially achievable with next-generation ultra-fast techniques. X-ray free electron lasers with higher repetition rates, combined with improved sample delivery and heating methods, promise more detailed mapping of the phase diagram. The nature of the glass transition in water remains controversial. Whether water has a single glass transition or multiple transitions corresponding to LDL and HDL remains unresolved. Experiments on confined water suggest complexity beyond simple single-transition behavior, but confinement effects complicate interpretation. Advances in fast-scanning calorimetry and dielectric spectroscopy on bulk vitrified samples could clarify the situation, revealing whether LDL and HDL have distinct glass transitions. The role of quantum nuclear effects, particularly for hydrogen atoms, requires further investigation. Path integral simulations show that quantum delocalization reduces structural order and shifts phase boundaries, but quantitative impacts on thermodynamic properties remain uncertain. Neutron scattering experiments sensitive to quantum effects through isotope substitution, comparing hydrogen oxide versus deuterium oxide, could test predictions. Understanding quantum contributions is essential for accurate modeling from first principles. The heterogeneity of water at ambient conditions, whether transient nanoscale fluctuations or true long-lived domains exist, needs resolution. Small-angle X-ray scattering experiments with improved background subtraction and multiple scattering corrections could definitively test for ambient heterogeneity. If confirmed, this would imply that two-state character pervades liquid water across all accessible conditions, not just in supercooled regimes. If refuted, this would clarify that two-state features emerge only near the liquid-liquid transition. Connections between ice polymorphism and liquid structure deserve deeper exploration. The 20 known ice phases represent discrete samples of the structures available to hydrogen bonding networks. Whether liquid water samples the same structures as ice polymorphs or accesses additional configurations determines how directly ice studies inform liquid understanding. Computational methods that connect glassy and crystalline states through minimum energy pathways could map this structural landscape comprehensively. Applications to biology require understanding water in crowded, heterogeneous environments with multiple solutes and confining surfaces simultaneously present. Most studies examine water with single solutes or in simple confinement, but cellular environments are far more complex. Developing models that capture how multiple perturbations combine to determine local water structure remains challenging. Multiscale simulations coupling atomistic water models with coarse-grained representations of large biological assemblies offer one approach. The role of water in prebiotic chemistry and the origin of life remains speculative but fascinating. Did life emerge in warm ponds with HDL-dominated water or in cold environments with significant LDL populations? How did early catalytic molecules exploit water's structural diversity to accelerate reactions? Laboratory experiments recreating prebiotic conditions while monitoring water structure could provide clues. If LDL environments favor certain reaction pathways relevant to RNA or protein synthesis, this might inform where life originated on Earth or might emerge elsewhere. Extreme conditions, including temperatures above critical point, pressures above several gigapascals, and negative pressures, remain poorly explored. Supercritical water above 674 Kelvin and 22 megapascals shows properties intermediate between liquid and gas, with potential industrial applications in chemical processing and waste destruction. Whether two-state features persist into the supercritical regime, perhaps as remnants along the Wiedem line, could influence reaction selectivity and transport properties. Education and outreach face challenges in communicating water's complexity to broader audiences. Most people learn simplified models where water is uniform with single properties. Conveying that water fights itself, containing competing structures in dynamic battle, requires careful explanation, avoiding both oversimplification and overwhelming detail. Visualizations showing molecular structures, animations of fluctuating hydrogen bond networks, and interactive simulations where users explore phase diagrams help build intuition about why water behaves so unusually. The path forward requires continued interaction between theory, simulation, and experiment. No single approach suffices to unravel water's full complexity. Theorists must develop models making testable predictions, Simulators must create accurate force fields and efficiently sample rare events. Experimentalists must devise techniques accessing previously forbidden regimes. The success over the past 2 decades in confirming the liquid-liquid transition demonstrates the power of this integrated approach. Future breakthroughs will come from similar collaborations across disciplines and techniques. Water's two-liquid war determines properties of the most important substance for life and technology. From the density maximum allowing aquatic ecosystems to survive winter, to the hydrophobic effect enabling protein folding, to the anomalous heat capacity moderating Earth's climate, consequences of this molecular-scale conflict shape our world. Understanding why water fights itself transforms it from a familiar yet mysterious substance into a comprehensible system whose strange behaviors arise from competition between geometric ideals and thermodynamic reality. The tetrahedral structures preferred by hydrogen bonding clash with entropic demands of liquidity, producing the rich phenomenology we observe. The journey from Röntgen's 1892 hypothesis of 2 molecular forms to the 2020 experimental confirmation of liquid-liquid transition spans over a century of investigation. Each generation of scientists added pieces to the puzzle, from Bernal's structural models to computer simulations revealing critical points to ultra-fast X-ray experiments capturing phase separation in action. We now stand at a unique moment where fundamental questions about water's nature are being answered, not through speculation, but through direct observation and rigorous theory. Yet much remains to discover. Water continues challenging our understanding and rewarding careful study with new insights. The two-liquid framework provides powerful organizing principles, but details require further refinement. Practical applications are just beginning to exploit this knowledge. As techniques improve and our understanding deepens, water will continue revealing secrets hidden within its molecular architecture. The war between low-density and high-density structures will occupy scientists for decades to come, each new discovery illuminating another facet of how and why water behaves as it does. If you found this exploration fascinating, consider how extraordinary it is that this common transparent liquid contains such hidden complexity. Every glass of water you drink hosts billions of molecules engaged in structural combat, constantly switching between states as thermal energy breaks and reforms hydrogen bonds. This molecular dance, invisible to the naked eye, determines water's unique properties that make life possible. Understanding this dance represents triumph of scientific inquiry, revealing that even the most familiar substances harbor mysteries worth pursuing. If you enjoyed this deep dive into water's hidden life, hit that like button and subscribe for more explorations into the science that shapes our world. Share this with anyone curious about why the universe works the way it does. The two-liquid war rages on, and now you understand what's really happening in every drop of water around you.